All right, I'm going to go ahead and get started just so we can make sure we're on time for the online people who are joining from various parts of the world. So in case you don't know me, I'm Alice Duvivier. I'm one of the Polar Climate Working Group co-chairs. Our other co-chair is Ed Blanchard-Rigglesworth, who I think is on a plane to New Zealand right now. And then Dave Bailey, who's our liaison. And then the Ocean Model Working Group co-chairs are Gustavo Marquez, who should be here at some point this morning, and Ian Grooms, who will be here later this morning or this afternoon. But we're starting kind of the meeting as a joint session, and then there'll be a split this afternoon. So I'm just here to welcome you and give some initial logistics. So the first, welcome to people who are online and everybody here in the main seminar room. The code of conduct we have here, we want everyone to have an equal opportunity to engage online and in person. So I'm going to try to follow any questions that are in the chat, and we have others monitoring that as well. But overall, we want people to be respectful, be collaborative, consider differing opinions, communicate openly, and be mindful of others. If you're here in the room and you need to join the internet, you maybe already figured this out, but there's a UCAR visitor wireless that you can join. You'll have to do a register before you get full access, but that should be fine. And then if you need any to contact anyone during the meeting, I have all these emails here. You probably got them all in your registration, but Elizabeth Faircloth, I want to thank her and the other admins who have done so much to organize all the logistics of this. If you're in person, there are admins sitting at the table outside that you can ask questions to also. And then you can email me or Dave or Ian or Gustavo. All right, so a brief summary of what the structure is going to be like today. So we have joint sessions this morning, and the focus of these topics are on wave-ice interactions, and that's here in the main seminar room. There'll be a break from 10:30 to 11. I know this is a pretty long 2-hour period to go without a break, so if you need to go, just run out and come back. It's mainly because the seminar timing made it a little awkward to try to have a different break in there. So there will be a break between 10:30 and 11, and there will be food outside and welcome and casual chatting before the seminar, which is going to be a remote seminar by Chris Horvat from Brown. And then we'll have lunch. We have an hour and a half about for lunch, and then we'll rejoin all of us together again in the main seminar room this afternoon, where you'll hear more about CESM3 development plans, state of the model, that sort of stuff, and we'll have a discussion at that period too. So we'll have a discussion this afternoon or this morning before the break, another discussion this afternoon. And then at the 3 p.m. end of that session, there will be a break, and then we'll split, and the Polar Climate Working Group is going to move to the Damon room, which if you don't know where that is, you can follow me or Dave or Marika or someone here, but basically you go up the stairs, take a right, and you kind of go around to this nice room at the back of the building. And the Ocean Model Working Group is going to stay here in the main seminar room. And we wanted to let you know that there will be an optional self-pay gathering this afternoon at Southern Sun. Southern Sun only accepts cash. I have been told to let everyone know it's Stout Month, so if you like stout beers, then you will be happy. The Ocean Model Working Group is going a little bit later than the Polar Climate Working Group, but we can all convene there when you're done. I think happy hour technically ends at 5, so just to be aware. And then tomorrow, the two working groups are going to be split again. The Polar Climate Working Group will be in the Damon room again, and the Ocean Model Working Group will be here in the main seminar room. And just a couple facilities comments. There are water fountains around. If you're not from here, try to stay hydrated because of elevation and stuff, and it's been an absurdly dry winter. For food, there will be food at the breaks, but the cafeteria sells lunch, and you can pay with a credit card. And then restrooms, this is a little bit out of date, I found this morning. There are men's and women's on the first floor, so if you go out of the main seminar room, it's a choose your own adventure if you go up or down. If you go down, the men's is on the left, the women's is on the right. And then if you go up, there's a single-use accessible restroom if you take a left, and then there's a men's restroom if you take a right. The women's restroom on the second floor is under construction of some sort. And this is the last slide, but just some goals of the meeting. We're having these joint sessions because we want to increase collaboration between the Polar and the Ocean Model Working Groups, especially on some of these new science opportunities like waves and how they're impacting the whole Earth system. We also want to get community input to inform model development and experiment design in CESM3 and after that release, and we're trying to reduce meeting fatigue so you don't have to go to all of these meetings. The individual sessions by model working groups will be more traditional model component development and community studies or results that are maybe a little bit more just polar focused or just ocean focused. I think everyone got this in an email, but to make sure you know, the meetings are going to be recorded. So, it should be available online later. And in this room, there's power under the seats. In the Damon room, there's power in the center of the table. And then they have now installed these barriers, but they really don't want us to touch this screen. So that was something I had from a previous meeting. So I think that, and this is the last slide. This is if you want to sign up for the CESM newsletter or other CESM communications, we have these links here. And then if you're social media inclined, there are ways to tag NCAR or follow NCAR and CESM, CGD, all of that kind of stuff here. So I think that's it. So without further ado, I'm going to invite our first speaker who is remote. It's Letty Roach. So Letty, one last thing, in the seminar room, when we're asking questions, the ceiling mic should be on. So they're going to let me know in the back when they get turned on. If you have questions, I'll call on you, and then online you can just unmute yourself and I'll let you know when you can speak. But the speaker will have to have a microphone. So, all right, I think that's it. Letty, go ahead and share and take it away.
Hello, can you hear me? You can hear me? Can you hear me? You can't really hear me? Hello?
I can hear you.
We can hear, okay, people online can hear me. Can people in the room hear me?
Online we can hear.
What about in the room?
In the room, we can hear you too. We're good now.
Okay.
We see the screen. Okay.
Okay, sorry about that. Hi everyone, thanks Naomi, and thanks for letting me join online. I've just got a few slides here to give a bit of an update on ocean surface wave interactions with sea ice and CSM3. Just to introduce this, one of the key challenges in representing sea ice in climate models is that we have this very complicated material with flows of different sizes, spanning many orders of magnitude, and we need to be able to represent this material in a continuum model with grid cells maybe on the order of 10 to hundreds of kilometers. And so most sea ice components in climate models use the sea ice thickness distribution to give some sub-grid scale information about sea ice. So this function G of H describes the area fraction of sea ice belonging to different thickness classes. And it evolves in models according to advection due to a momentum balance, thermodynamics, here represented with a meltal growth function F, and ridging or rafting. So then as a further step, in recent years, a few of us have worked on the sea ice flow size and thickness distribution. So here F of R and H is the joint distribution describing the fraction of grid surface area covered by sea ice with thickness between H and H plus DH, and lateral flow size between R and R plus DR. So that's a radius. And this theory was introduced by Chris Horvat, who's here. And in a similar way, we can write an equation that describes the evolution of this distribution subject to advection, thermodynamics, mechanical interactions, and wave fracture. So I work towards implementing this model in size 6 ice pack. With this implementation, we had no feedback between the flow size distribution and dynamics or mechanical interaction. So the flow sizes are just affected passively by the sea ice momentum. What we have updated since those earlier papers is a new wave fracture scheme, and so I'll come to that towards the end. And also just to mention that there are other kind of implementations of this type of approach underway in different models. So I'll show a few plots from a development simulation with CSM3, and here I've used the BHIST 271 configuration. So this has the atmosphere and ocean, then we have size 6 and wave watch coupled by via the flow size distribution. So this coupling introduces a few new processes. First of all, we have wave attenuation in sea ice. So this is the damping of wave energy by sea ice, which is quite complicated. It depends on the properties of the sea ice. And so there is a fair amount of uncertainty here. But overall, we have a damping of high frequency waves. So you get these quite smooth swells like you see here in this pancake field. And what we've used in the model is the Malin et al. Flow size dependent attenuation scheme. And so this means that we have waves within the sea ice. So at the right, I'm just showing March 2010. The colors are significant wave height. The yellow contour is the 15% sea ice concentration contour. And so if you were to follow a straight line, this is just along the 0 degree longitude, then this is what I show here in the line plot at the bottom, that you have large significant wave heights in the open ocean. These start to decrease as you move towards the sea ice. And then you have this reduction down to 0, but you have some area within what is often called the marginal ice zone, where we have lower sea ice concentrations and we have quite significant wave heights present. Then on the sea ice side, when waves are present, this affects the flow sizes that are formed during this process. And so the idea is that if you have no waves, you would form very large flows. But if you have some wave activity, then you would set an essential limit on the size of flows that can be formed. So if you have strong wave activity, you would form these very small ice flows called pancakes. And we made an attempt to calibrate this with in situ observations. Then in the model, and here I'm just showing October 2013, you see that the perimeter per unit area, so this is really the total area of ice around the edges of flows, a measure of the fragmentation. This is quite strongly increasing in areas where we have ice growth. So this is really a very effective process for increasing the perimeter. We also have flow welding, so we represent this in the model just at the current state, at least, just in a simple way by allowing flows to freeze together according to their geometric probability of overlap by a coagulation equation. And this we also made an attempt to calibrate with in situ observations. And we see, if we look at the representative radius, which is like a mean flow size, the tendency here, again in October, so in freeze up, you'd see this is acting to increase representative radius. And we see that it's effective in the central ice pack, and it can cause, it's really the central process by which large flows are created. We also represent lateral growth. So here, flows are increasing in size. So there's a redistribution amongst the flow sizes towards larger flow sizes, as well as a change in the concentration of the ice, according to the volume of new ice growth in what we call the lead region per time. But this turns out to actually have a very small magnitude in the model, so I didn't include it here. It has very minimal impacts on perimeter and concentration. But then its opposite process, so the lateral melt, is significant. So this is really just doing the opposite, going to smaller flow sizes and also reducing concentration, where we use the same lateral melt rate as would be in the standard model with no flow size distribution, which assumes a constant flow diameter. And we find this has significant impacts on sea ice concentration. And so it's really the main way in which we have a feedback between the flow size distribution and the rest of the model. So this is effective in melting out small flows. So that's the magenta areas on the edge of the ice pack, and will also change the overall concentration and thickness of the sea ice. And then lastly, there is fracture of sea ice by ocean surface waves, which acts only on the flow size distribution, so it's not affecting concentration or thickness. This was described by Dumont et al. As being according to one of two limits. So you could assume that sea ice is completely rigid, it's not flexing with the sea surface, or that it's completely flexible with the sea surface. And they suggest looking at both of those limits and then computing either or resulting from the largest of those two. In practice, the second one is what got picked up sort of by the community, and so using this assumption that the sea ice is completely flexible. And so this is what was used by Chris in 2015, and then we also implemented in SICE in the later papers. But we knew this was some sort of approximation that we weren't really happy with, and it also gave us some quite large strain values that didn't seem to be very physical. So in some recent work led by Bruno Tremblay, we developed a new approach based on thin elastic plate theory. So now we're not making either of those extreme assumptions, but actually calculating an equation for the deflection of the ice relative to the sea surface that we found we can solve analytically. And we recover the both of those extreme limits that are separated by this characteristic length scale with capital gamma. And so the structure of the parameterization is still quite similar to what we had before. We're still computing a strain, but it's having a bit more of a physical basis. And if we look at some of the strain results, this is computed from just sort of idealized simulations with a single flow. Then you can compare the fully flexible scheme on the left. This has quite high strain values, going up to 0.04. We also saw with this scheme that if you have flows of size of smaller sizes, so here the flow diameter is 50 meters, that we have increasing strains as thickness increases, which we did not think was really realistic. But with the thin elastic plate scheme, then we have in this blue line we have a decrease in strain with increasing thickness. And our flow sizes, our strain sizes are on the order of 10 to the minus 4, which is still maybe a little large, but it's much closer to the kinds of observed values that we saw from, for example, Langhorne et al. 1998. And so this scheme has been coded up and is now active in this CSM3 development version. And it's still kind of active area to keep doing some more analysis on that. And then just to wrap up, just to show that in this historical simulation, there's some indication that these processes might be becoming more and more important. If we look, for example, at the significant wave height, I've just taken a September decadal average from early on in the satellite era towards the end of the simulation. And so you can see that you have these increasing wave heights, both outside the sea ice edge and also somewhat also within the sea ice. So here at the right, I show the difference between those two panels. And you see that you have these large significant height increases, for example, in September around the ice edge. And so to end with some questions, so hopefully with this new capability, we can go some way towards better understanding how ocean surface waves and related sea ice processes are changing and will change in the emerging Arctic and Antarctic. How significant this feedback, so really the main one we're representing is this lateral melt feedback with fragmentation. How significant is that in the fully coupled model? How can we further improve process representation? And how can we compare with limited observations? So then to go towards the discussion in terms of needs or things to kind of put on the table, I think, so that now we've got now that the development version has all of this physics included in it, I think we will need some simulations with things turned off as a baseline to compare against. So maybe simply just having no FSD and no wave ice interactions would be the simplest case there. It would also be nice to have a constrained simulation to compare with observations. So maybe something like a data atmosphere model. And then maybe we would also like to discuss a bit more as a group the output. So I noticed just in putting these slides together that there isn't very much in terms of the wave output. And so just making sure that we have everything sort of turned on that would be useful there. So that's all I have. Thanks again, and happy to take any questions.
Are there any questions in the room for Letty? Not yet. We're saving it for discussion. People are still waking up. All right, we have a question. Alec Petty has a question here.
Yeah, thanks for the great talk, Letty. I guess it is your hope that it also, you can somehow track the size of the marginalized zone, and I know there's different metrics to do that. Do you have any thoughts on that? Like, I guess there's the kind of wave affected definition, and then there's the kind of just more concentration based, and if you've looked at how that's changing with and without the scheme.
Yeah, I mean, I think, there's been quite a few different studies who've used different kinds of definitions, and I guess it really depends what which one is appropriate. I think depends on what your aim is, and so I think like moving towards doing some comparison with observations, it would sort of really depend on what observations we're looking at and what we could do that kind of gives us the closest apples to apples comparison, I think.
Yeah.
Thanks.
And we have a question online from Mitch. Do you want to unmute Mitch and ask?
Yeah, sure. Thanks, Letty, for that. It was a great talk. I was just curious how the adding the wave-ice interactions affects the computational cost of the model.
Great question. I do not have numbers really very close to hand. I think possibly Diajeng has some in her presentation. It definitely is more expensive. The wave fracture is really quite expensive. We did find that moving to the new scheme saved us a little bit in computational costs because you're just not computing as many times. You're not computing wave fracture so much because the strains are lower. So that is positive. But yeah, I think there are others here who can give a bit more quantitative answer to that, perhaps.
Great. Okay, thanks.
Thanks.
I think when we were first estimating this to tell Dave Lawrence, the chief scientist, it was something around like 10 to 15% more expensive of the cost of the whole model, and it was primarily the wave fracture. So Diajeng will talk more about that. But I know it's different for different models, and we'll hear a little bit about that later too. All right, so I'm going to introduce our next speaker. We're getting her talk up. So our next speaker is CC Bitts, and she's going to talk to us more about the wave-ice interactions in CESM as well.
Thank you. Really great talk, Letty, and we didn't coordinate enough because I was in the Arctic until Monday. So I'm sorry about that. But I'm going to also talk about recent work in the CESM, and I think I'll just get right to it since Letty already gave a lot of great background and just show you the basic impact versus our old method, which was to just prescribe all flows at 300 meters. And the biggest impact on the sea ice is that it shifts what would be lateral versus basal melt, which was formerly almost entirely basal melt, into about 50-50. And that's because the flows are much, much smaller than 300 meters at the edge, and therefore their perimeter to base area ratio goes way up, and that gives rise to more lateral melt. And when we compare the impact on the sea ice itself, it changes the ice thickness and the ice concentration in expected ways, where it's thinner and less concentrated at the ice edge, especially. But I really wanted to get to our recent simulation. Letty also presented briefly a little bit more depth and show you how it looks. So this is the recent 1850s control simulation and 10-year means here. And what we're seeing is just a beautiful sea ice concentration, and I'm really thrilled to see that after a long development period with some bumps on the way. And this looks great to me. Of course, we're comparing against the modern record here, so we don't expect perfect comparison by any means, but it's in the direction we expect. And the significant wave height, as a result of the wave ice interactions, now you can see the wave height is dramatically different in the presence of sea ice, with strong attenuation by sea ice, of course. But nonetheless, there is still wave magnitude at the marginal ice zone in the edge of the sea ice. And this has these consequences that are dramatic for the flow size distribution. I decided to do one experiment, of course, starting it yesterday, of a perturbation run where I turned off the attenuation in the sea ice. So let me rephrase that. It's completely attenuated in the sea ice now in the second run in the middle frame here. And it's pretty hard to see the impact on the ocean mixed layer depths by eye because they're already pretty small in the presence of sea ice. But a difference plot shows that the mixed layer depths are really about 50% smaller if we have no wave mixing in the presence of sea ice. Love to talk to oceanographers about better ways to characterize the impacts on the ocean if you can talk to me afterwards. But back to what the sea ice itself looks like, Letty did show the representative flow size radius in the northern hemisphere. Here it is in the southern hemisphere. And of course, she also got the question of how does this compare, or does this give us an opportunity to give a different measure of the marginal ice zone, which is generally known as the wave-affected part of the sea ice. And you can see the representative radius versus the sea ice concentration are not mapped one-to-one. And so it definitely does give us an opportunity to have a more faithful definition of the marginal ice zone. I've also shown some flow size distributions here for your information. Really, what we're trying to do is actually simulate this 15 bins of flow size as a probability in each grid cell of occurrence of these different bins. And I did some conditional averaging on the 15 to 18%, 80% concentration, and 80 to 100%. They're not that different. I was actually expecting them to be more different. But one thing you may notice is this large truncation error at the very end where the magnitude goes way up. And that's something we would like to improve upon. So this is the basic CESM3 model as it stands. And I'm going to talk about ways we'd like to improve the flow size distribution. So that basic pattern is also shown here in turquoise from our earlier work. And it was shown versus observations to have some bias. And there's one other model in here that basically is a relaxation to the observations. So it kind of gets the right answer better, where we're really trying to do this at a very process-oriented level. So we're basically working on ways to improve. And one thing we would like to do is improve that, bring down that truncation error, but there are lots of other ways we'd like to improve. One is that we're not getting big enough flows in the Central Arctic, just simply because we didn't have a bin size that went very high. So we're going to extend the bounds in the simulations I'm going to show next, which are all improvements on what we have in CESM3. We'd also like to potentially get a better accuracy in the wave fracture that he mentioned. It depends on this new physics that allows the ice to bend, and that discretization is at 4 meters, and flows are now down to 1 meter. So we're not really getting very accurate characterization of the fracture. So we're going to think about how we can do that better. Currently, we don't account for deformation, so that would be like the strain rate on the sea ice itself doesn't cause wave fracture. We've been improving that and taking that into account. We've also been modifying the welding kernel to try to get more, faithful welding. And basically what happens in this model today is that waves fracture it and then it welds back and forth very fast and probably not as observed. What we see in observations is kind of a more steady pattern of the flow size when we look at MODIS images from one day to the next. I don't actually think a lot of this has a huge impact on the ocean. I think we got the basic science right, but we'll find out though, I guess, once we really implement these in fully coupled simulations. But somebody asked about the timing and the basic CESM timing. Now, these are just relative values. We calculated about 11 seconds per model day for this discretization at 4 meters. So we thought, okay, well, how does this change if we do a better job at discretizing, just doubling it? And it increased the model time by an order of magnitude. and I don't think we increased the number of processors, right? So that we might have been able to parallelize a little bit better. Anyway, another thing we wanted to do was extend the bounds, and I mentioned that's motivated by something that Gerard's going to talk about next, but it's to better have deformation effects in the central Arctic, and that also increased the model a lot of times. So we were like, we're being defeated by what we really want to do here, and so we implemented an emulator of the wave fracture process itself, and we did this using a simulation at 2 meter accuracy. So we were able to emulate a more accurate version of the scheme, and then when we do that, the emulator is much faster than even the coarser resolution. So these toasts floating on the ocean here are meant to represent the 12 bins. And what happens in the wave fracture scheme is each bin can fracture into smaller categories or smaller bins. And so say flow bin 11 can fracture, and when it does, its probability of fracturing where it goes is shown here just for some example, and a different example. So this is what we're trying to emulate, this so-called fracture histogram. And this is the work of Gerard, so he will be able to answer all your questions. But what he did was, based on the method that Horvat and Roach also implemented previously for the Horvat and Zipperman wave fracture scheme, we're now kind of repeating something similar for the new Tremblay and Roach scheme. So we have a 2-step scheme where first we have a neural net that asks, is it going to fracture? And if it fractures, then another neural net that is engaged to actually calculate that histogram itself. And Gerard has implemented this in CESM, not fully coupled simulations yet, but at least coupled with waves. And the emulator is doing a fairly nice job at predicting the kind of histograms that the full model physics does. By the way, we only do this for the 6 largest flow bins because those are the ones that are very costly. We just kept the physics for the smaller bins because they're small, and the actual physics is pretty fast, maybe even faster. But the full result on the flow size distribution is really excellent. There's really hardly any difference between the emulator and the physical based model. And that extends to other sort of derived quantities like the representative radius and the significant wave heights. The last thing, how much time do I have? I kind of start another minute. But I mentioned that we wanted to kind of adjust the welding, and this is the coagulation theory that Letty implemented from Filbert and Lancelot. And what they did when they did this was to choose a kernel here. The A is the kernel. That was the product of the areas of 2 flows, and we adjusted that to be the product of the perimeters. So that had some significant impacts, and I won't talk too much about it since I'm running out of time, but I thought I'd show just one last video of what this looks like and why I'm frustrated by this. Is just 1 month, and basically it just moves the ice edge where that fracturing is occurring and where the welding is occurring so rapidly that it would, if we had an image like the satellite image above, it would just be fracturing and welding and fracturing and welding. Whereas if we look at day-to-day MODIS images, they're pretty stable. So I still think we have room to improve. So with that, I'll just summarize, if I could get my summary slide up, and say, I think that we have currently a good model with pretty sensible results. The ice edge looks great. There's lots of ice wave interactions to explore. And I'm also really excited about looking at how this will play out in 21st century simulations. But we're working on improving the spatial heterogeneity in the Central Arctic. We want to implement a dynamical flow size interaction. So we'll have the flow size influencing the rheology. Gerard's been working on that. He'll show some really great results. We needed to extend the flow size, so we needed to speed up the model with an emulator. That's working really well. Finally, I'll just note that I had to originally adjust the wave numerics in WaveWatch 3, and I'm not going to talk about that today because it would bore you to tears, but I'd love to tell you if you are interested. Thank you.
All right, do we have any questions in the room? We'll start with Dan.
Susie, I was wondering, do you expect needing to retune any of the parameters if you move to different resolutions in the ocean?
No, I mean, you're saying parameters in the sea ice
Yes.
flow size? No, I really don't think so. I mean, because these flows are at the meter scale. Yeah, I mean, at some point we would have the largest flows in the tens of kilometers, and we could have resolution finer than that. Seems like a bit of a mismatch, but since it's a subgrid scale parameterization, it'll run just fine.
All right. Online? Are you doing that for online?
I can do it for Ed. Do you want to go ahead?
Hi. Yes, hopefully you can hear me. Great talk, Cece. Thanks so much. And I was sort of fascinated by those changes in the ocean mixed layer depth that you showed. And this is a question I think maybe also for Letty. I was wondering if you've looked at the high frequency variability and whether once you have active wave ice coupling, whether you see that sea ice variability go up as you have either big swells or maybe kind of calm seas, in time.
I have looked at that, Ed. I didn't look at it in these simulations since I've only been back from the Arctic for less than 48 hours. So I haven't done it with the most recent simulations, but in our developmental simulations, it does increase the variability in the sea ice. So we have more extreme 5-day anomalies in the sea ice with the wave interaction, sea ice.
I wanted to ask about what your thoughts on the wave model resolution. I mean, because in CSM3, we're running a coarse 3-degree resolution.
Please increase it.
Yeah.
You can see this dramatic gradient in the significant wave heights at the ice edge. This is being resolved at 3 to 4 degrees or 3. Bad. Not good enough. So we would like that to be finer. Right now, it's of course being interpolated to 1 degree when it goes into the sea ice model. So sea ice is seeing a finer resolution, but it's super smooth. So please increase it. And tell us how. Moment. Oh, sorry.
Well, we haven't. I want to keep us on schedule because we have remote people, but there is a discussion at the end of this. So maybe some of the questions, David and Moma, can be brought up then. Is that okay?
But it's
Okay. All right. Our next presenter is online, and it's Dia Zhang. She's visiting us from Europe. So, Dia Zhang, are you able to unmute and share your screen?
Yes. Can you hear me?
Yep, we can hear you.
Can you also see my slides?
Yep, looks good.
Perfect. Okay, greetings from Germany, and thanks for having me here. So I'm Dia Zhang at Mojo. I'm a PhD candidate at the University of Bremen, and last year summer I visited Dave Bailey and Marika at NCAR, and we started with this new project, which is about developing a machine learning-based parameterization of sea ice flow parameter for CESM. So Letty and Cece, they already gave the physical background of the flow size distribution. So basically, sea ice flows vary greatly in size, ranging from centimeters to kilometers, and the size of flows is impacted by various physical processes like the melt and growth of individual flows, the flow welding, the flow fracture, and the new ice formation. So why do we care about the size of flows? As Cece and Letty also already mentioned, it's important for the lateral melting. So specifically, lateral melting is parameterized as follows. So the change in sea ice fraction due to lateral melting is defined as the product of the lateral melting rate, the total perimeter of flows per unit area, and the sea ice fraction itself. To give you, to illustrate what the total perimeter actually means, let's take a look at the schematic here. So here you see two model grid cells where the sea ice concentration is the same, but in the lower grid cell, the perimeter is way higher because you see way more smaller flows. So essentially, the sea ice here is more fragmented. So simply put, the higher the perimeter, the more fragmented the sea ice is. So the perimeter indicates how much sea ice is exposed to the ocean at the flow edges, and therefore the available amount for lateral melting. And in previous CSM versions, the perimeter is set to a constant. So yeah, Letty and co-authors, they implemented the flow size distribution, the FSD, which will be turned on in CSM3 by default, which takes into account all the flow size related processes. The problem is that it is computationally expensive. So the goal of the study is to emulate the FSD, so taking into account all the flow size related processes to parameterize the flow parameter. So we want to reduce the computational cost compared to CSM3 where the FSD is turned on and improve the representation of lateral melting compared to CSM3 where the FSD is turned off. So this is the workflow of our study. So first of all, we generate training data from CSM3 outputs, and then we train a multi-layer perceptual neural network, so very simple neural network architecture. And yeah, we use the CSM model output for training the neural network. Then we perform sequential feature selection, which is a machine learning method to get a ranking of the most important input features. And based on that, we develop parsimonious models, so models that perform well with as few inputs as possible, balancing model error and complexity. And the main goal is then to couple the parsimonious, the best performing model online to CESM3. So the training data, so we perform a fully coupled pre-industrial run, turning the FSD on with a spatial resolution of 2/3 degree, and we output instantaneous half-hourly data and simulate 4 years. So the first year is used for spin-up, the second year for the training, and the last 2 years for evaluation. And we use the following candidate variables that are available in CSM3 where the FSD is turned off, namely sea ice fraction and volume per unit area, so from the ice thickness distribution, sea ice velocity, ocean heat content, sea surface temperature, ocean currents, significant wave height. From the atmosphere, we use winds at 60 meters, 2 meter specific humidity, and air temperature and atmospheric ice stress. And our target variable is the flow perimeter per unit area. To give you a physical intuition how the flow perimeter looks like, here you see spatial maps and the monthly distribution for each hemisphere. So basically you see that in the northern hemisphere, we have a lot of low perimeter values, which represent less fragmented multi-year ice, and then we also have seasonal ice in the northern hemisphere, whereas in the southern hemisphere, we have mostly fragmented seasonal ice. Okay, let's jump into the results of the machine learning pipeline. So here you see the ranking of the most important features derived from the sequential feature selection. The most important feature is the subgrid scale ice fraction, followed by significant wave height, then the ice volume per unit area, ocean heat content, and SST. Here you see the monthly root mean squared error for different models. So here I'm comparing the full set model, so the neural network trained on all the candidate variables. SFS3 model is the model trained on the first 3 input features, and then also SFS4 and SFS5 for the other input features. And what you basically see here is that looking at the global RMSE, you don't see significant differences, but looking at the northern and southern hemisphere each, you especially see that adding the ocean heat content improves the neural network prediction during the melting season in both hemispheres. Here, I'm also comparing the SFS5, including the ice thickness distribution, and then also only taking into account the mean, so the mean ice fraction and the mean sea ice thickness in each grid cell. And what you basically see here is that the including the ITD is crucial, so for better NN prediction. Now let's take a look at some time series. So I just picked some locations in the northern and southern hemisphere. So you see that the predictions are quite well. Here, for example, you see this sudden jump from low to high perimeter value, which is associated with wave fracturing. And this is captured quite well with by the neural network. But what also happens in other locations, you see that the neural network prediction is very noisy, and we are still working on improving that. Okay, online coupling. So for that, I use the CSM3 Alpha 07F tag, simulating only 2 months just for testing. So if you turn the FSD off, you get 5 seconds per modeling day. Turning it on increases the computing time to 1.52, which is about 30% of the whole size model. And then plugging in the machine learning based parameterization, it decreases the computing time by 0.82. And for the coupling, we used FTorch, which is the Fortran PyTorch bridge developed at ICCS Cambridge. And this is the standard library in the machine learning enhanced version of CESM. So the machine learning based parameterization is faster. So now I already come to the summary. So we see an overall good performance of the neural network using the 5 most informative input features, which are the subgrid scale ice fraction, significant wave height, the ice volume per unit area, the ocean heat content, and the SST. Including the subgrid scale information is crucial for NN prediction. We see that the predictions are noisy, which we still need to improve. And coupling the machine learning based parameterization using FTorch is faster than the FSD. So next steps and ideas. So we also want to include an additional step, which is the neural network classification, where we basically want to classify first whether we have pancake ice or not. So pancake ice is represented by very high values, so above 0.7. And if that's the case, then we just assign like a fixed high value. And if not, then we perform the neural network regression. And we do this because we still see in some time series that the neural network is fails to predict these high values. Yeah, and also another idea from the ML people that I got was to train generative models, which takes into account the underlying distributions of the inputs, and that could potentially overcome the noisy predictions. And of course, also evaluating the machine learning-based parameterizations online. So yeah, thank you for your attention.
All right, we have time for a question or two. We have one in the room.
What is the relevance of wave direction for your results?
Wave direction?
The wave height does not account for direction. And I imagine that if you have a convergent waves into the shelf, you should have some importance to your simulation.
Yeah. I mean, the only information that we get is the significant wave height. So, yeah, I don't know if Letty has an answer to that. Yeah, I'm not sure.
Good question. I saw Will Gregory raise your hand online. So why don't you go, Will, and then after that, we'll move to the next.
Hey, yeah, cool talk, DJ. Can you hear me okay?
Yes, yeah.
Great. Yeah, I was just curious. Yeah, on this slide, actually, you mentioned here that you've got a 4-year training or 4-year simulation with half-hourly input. What was the motivation behind that? I'm just kind of wondering if the noisiness you're seeing is by learning these half-hour snapshots, and if you would reduce some of that impact by maybe still learning half-hour snapshots, but implementing them as like a running mean of those snapshots or something where, over 6, I don't know the timescales of when these things are kind of critical, but I don't know if that would help.
Yeah, so the model time step is 30 minutes. So we wanted to make sure that we really learn like the actual output of the FSD. But yeah, I haven't mentioned it, but for the training, I subsampled the data. Because from each month I got 10 to the power of 8 data samples, which is a lot. So I subsampled them to 1 million per month. So yeah.
Okay.
Yeah. But yeah, we've already thought about taking the mean, but when it comes to practical implementation into CESM3, we were encouraged to use instantaneous data first, and then yeah. So,
okay.
Yeah.
All right, cool. Thank you.
All right, thank you so much, Diajing. All right, our next speaker is Geraint Webb, who Cece mentioned earlier. So now we'll hear some of his work.
So yeah, hi everyone. My name's Geraint. I'm a student working with CC. I'm going to describe some more. I'm sorry, can you turn on your mic? Or was it not turned off? I thought it was. Is that better? Thank you. Sick. So I'm going to be talking about my work on a new parameterization describing the health of a sea ice flow and its potential to influence wave fracture. So first of all, we have to ask the question that's been asked a lot today. What is the flow size distribution? And I'm sure we're all learning. So if we look at this observation to the right, the flow size distribution quantifies the probability of finding a flow of a given size over a given region. So if you look at these observations over the Canadian Basin, we have a number density on the y-axis and area on the x-axis. You can see that over this domain, you're very unlikely to find very large flows, but you're very likely to find very small flows. And generally it follows, as we've mentioned before, this power law, except the slope can vary depending on where you are and what time of year it is. And so I'm going to kind of skip over this because we've talked a lot about this, but SICE models the FSD with 12 bins. SICE prognostically models 5 processes that affect the flow size distribution. And Letty did a great overview of these. So new excavation, lateral growth, lateral melt, welding, which I'm just going to remind everyone is when 2 flows come together and coagulate into a singular flow, and wave fracture. And so what we're going to be doing today is we're going to be introducing another process, flow deformation. and a new tracer, flow health, to try to tackle this homogeneity in the Arctic and from this flow size distribution that CC mentioned. And so what is the mismatch between sites and observations? As CC did a great job showing this as well. So we have this large truncation in the final bin. The final bin is accumulating lots of flows, and this is occurring because of welding. Flows are welding to the very last bin, and they're all accumulating there. So we get this big increase. And so what we're going to be doing today is we're going to be trying to target these last few bins. And so we're going to be looking at ways that we can reduce the magnitude of this truncation between the last bin and the penultimate bin, or the second to last bin. So the first mechanism that we're going to use to approach this is going to be flow deformation. So here's an example of a flow deforming. So if you imagine that there is a divergent ice velocity field, and you can imagine we have this huge flow on the left-hand side here. And so that is being pulled apart by this divergent ice velocity field into many, many smaller flows in the center of the image. So this very large flow is being pulled apart into many smaller flows. And so Niels Hudder did a lot of work on this. And so he came up with a model that we can put into SICE, a mathematical model, I should say, that we can then implement within SICE to represent this process. So what he did was he took SAR imagery a day before a flow deformation event and a day after the flow deformation event, and then compared how did the flow size distribution change between these two different events. And so when you do that thousands of times, you do that lots and lots of times, you can end up with something like this change function, or these observations of change in the top right here. And so this is for many different divergences. So some days it'll be very strong, a very strong flow deformation event, and other days it'll be a very weak deformation event. But as you can see, the general trend is very large flows are broken down to many much smaller flows. And then so what Niels did was he got a mathematical model, he applied this model, and we're going to take this function that he has down in the bottom right, and we're going to put it within SICE. So this function is a function of both the radius of the flow, but also of the divergence in the ice velocity. So how are we going to do this? We're going to have and how are we going to compare this? So the model setup for our little experiment is going to be a bit simpler. It's not going to be fully coupled. We're just going to use the CSM3, but we're only going to couple SICE with WaveWatch3. We're going to use the extended bounds that CC had mentioned. So instead of going from bounds out to, say, 1 kilometer in the default version, we're going to take our maximum radius out to 25 kilometers. We're going to have a prescribed atmosphere. We are, sadly, for many people in this room, going to be using a slab ocean. And we're going to do a 40-year run with an analysis on the last 10 years. And so what does this look like? Well, it may be a little bit underwhelming at first. So in the first column, what you see here is the control run. In the second column, what we're looking at is this with this flow deformation parameterization turned on. And the final column is the difference. And you can see there's a very marginal difference in March in the Northern Hemisphere, but it's not like blowing my socks off per se. And so it's only about 300 or 400 meters, and the maximum size of the flow represented here is 17.5 kilometers. So it's really not doing much. And this is getting at what CC was mentioning. So as these flows are being deformed, they're very quickly being rewelded, often within the same time step. They're just deforming, rewelding, deforming, rewelding. Conversely, when you look at September, so welding depends on it being cold enough to have this thermodynamic coagulation of two flows come together. You'll notice that it's actually a lot more negative. So there's no longer this welding tendency overriding the flow deformation. And then in areas where there's a lot of divergence, you can see there's a lot of loss of a lot of fragmentation of these flows. So that was a good sign, but again, it's still not perfect. And so what this looks like when you're looking at the flow size distribution, and when we plot it, and just for the Northern Hemisphere and the Southern Hemisphere, as you can see, that it's reduced the truncation between the final bin and the penultimate bin. So it has had an effect, but again, it's not that knockout that we were looking for. So to approach that, we're going to try to use something called flow health to help solve this truncation problem. And I'm going to just tell you how we're going to define flow health. So what is flow health? So imagine you have two flows sitting in the ocean, and they're sitting right next to each other. And they then thermodynamically weld together. So now you have one flow that is now much larger. But at the moment that is welded, you imagine there'd be a very small ice bridge between the two different flows, and it'd be the weakest at this moment. This is the weakest the flow would ever be. So if there was then a flow deformation event, or if there was wave fracture, you would imagine it'd be a lot easier for this newly formed flow to then break back into its constituent parts again. And so you would also imagine, though, that after a long period of time, they might end up with this healthy ice bridge between these two different flows. So the flows become a lot more healthy. So this is what we're going to describe. So this would be the most healthy a flow could be, and this would be the least healthy a flow could be. And so how do we represent this mathematically? We represent it very similarly to the FSD. So we have a flux convergence in both space, but also due to thermodynamics, so the flows can move thermodynamically. So if you have an unhealthy flow that then laterally grows, it will be equally as unhealthy the next bin as it was in the previous bin. But if there's a positive welding tendency, that should reduce health. So at the moment that two flows weld together, they'll be the most unhealthy they could possibly be. There's also going to be tendencies that will increase health. So you could have new ice. So you would imagine that if you introduce new ice to the system, it would be healthy, one would hope by this definition. But also wave fracture and flow deformation would actually increase health, potentially counterintuitively, because say you had two flows that weld together, well, now there's been wave fracture, they've broken apart. So now they're back in their constituent parts, which we're going to define as healthy. There might be a better way to do this, but this is just how we've taken a first stab at it. And then finally, there's a time decay term. So obviously we use an e-folding time about 180 days. And so the flows will heal over time. So what I want you to keep in mind is 0 is the least healthy you could possibly be. 1 would be the most healthy. And we're just going to look at grid cell averages here. So what our climatology looks like. So if you look at March in the Northern Hemisphere, in September in the Northern Hemisphere, so you look at March, you can see that flows are generally very healthy, where it's like perennialized, where it's thick multi-year ice straight north of Greenland and the Canadian archipelago. So this way it'd be most healthy. There's less welding, whereas areas where there's lots of welding in the marginal ice zone, so you can see this very dark light colors. If you can follow my mouse here, you'll see that that's because the waves are the flows are constantly being fractured by waves, and then they're re-welding, and they're being fractured by waves, and then they're being re-welded. And then so likewise, we can see this in September in the Northern Hemisphere. We can see similar things going on. So it's actually a lot more healthy, which you might be thinking, well, it's September. That doesn't sound correct, but it's actually just because there's not so much welding going on, so there's no way to reduce health, but there's a lot of wave fracture, and wave fracture is a tendency increasing health. So that's why it's kind of a little bit counterintuitive here. At the very, very edge, you'll notice that it's always healthy, even in the winter. And so this, you can imagine that these are flows that have been evected out into warmer water. So there's less, there's no longer the welding tendency, but there is the wave fracture. So cool. So that's what it looks like from a climatological perspective. And then so why even make this like big metric and this big tracer? What's the point? Well, it's because we're going to try to amplify both wave fracture and that flow deformation I just mentioned. So wave fracture at the moment, there's a critical strain. So there's a point at which when we calculate in our wave fracture scheme, that the flow will fracture into many different parts. But what if we could instead, if we had a very unhealthy flow, reduce this critical strain? And so so imagine this was the healthiest the flow could be, and it would not be fractured by the stream because it does not breach this critical strain threshold. But then if we reduce that because you had the most unhealthy a flow could possibly be, it would then be a lot more likely to fracture. And so we choose for just a good first pass, we just make it 10% of the value. So so we reduce the critical strain by to 10% of its original value. Likewise, we increase the flow deformation by about an order of magnitude of another feedback, and we also reduce ice strength. So this is the first time that FSD has been connected to the rheology of the model directly. And so when we do that, we get some somewhat interesting results. Again, we still have truncation in many of the seasons, but you'll notice in September in the Northern Hemisphere, we've actually reduced that. You'll also probably note that it is not following a perfect power law, so there's definitely more work to be done. But it is a good first approach at seeing what happens and how important welding is currently in our model, at the very least, in dictating this truncation error. And so how this looks like in terms of the representative radius as well is there's large decreases in the representative radius in all seasons. So if you look in this first panel in March, Northern Hemisphere, you might actually be able to start to see there's actually some gradients. Whereas if I was to compare to without using this health feedback, it would just be a very homogeneous, homogeneous world of uniform flows. And so you can definitely see that in September in the Northern Hemisphere. Likewise, we have pretty much uniform decrease in representative radius. And the only time we ever have an increase, you might be thinking that's a lot of red, is because we reduced the ice strength. So now the ice is more likely to advect, and it's just moved to a place where there was not that large flows in the past. And now there are large flows because they've just been advected that way. But yeah, and with that, I'll end future.
Do we have questions in the room or online for Grant?
Chris.
Oh, that might have been a clapping. I don't know. Chris, did you have a question?
I did not. That was an attempted clap. Sorry.
Moment.
I can
So there is the concept of damage, which is, I think, the opposite of health. Right, and they write it as a prognostic variable in that model. Would you be able to do that too? We keep track of health or in size.
At the moment, we only keep track of it for the 5 tendencies, but that you could keep track of it for something like damage. You could also do it for like if there was other thermodynamic effects that would also affect it, but you could do it on
for over time, right? And then there's healing properly and all these things.
I haven't thought about that, but well, yeah. Thank you.
David?
I was wondering if you've thought about basically other processes that join flows together. So particularly ridge formation at the edges of flows.
Yeah, so this is something we've thought about. So at the moment, it's basically we're assuming that this is how flows well together, and that first of all, obviously, there's not like a bunch of pancakes and then come together and make one giant flow, but also not like ridging or like rafting. But that is something that we have considered and something that we could include, but it's not actually currently included in like the welding parameterization. But if you were to include it in the welding parameterization, this is just taking the tendency from that. So you could change the welding parameterization as much as you wanted. You could include ridging or rafting, and then you could still have this metric coming out at the end. It'd be quite,
Last one, Nguyen online. Do you want to unmute?
Sure. Hi, thank you. So my question is about the first comment you have here. It said you use observation to constrain the model. My question is, because the flow size is so variable in terms of both spatial and the temporal scale, where your observational data source come from?
And that is a great question, and that's why it's in the future work section. That's what I would like to work out and do in the future. Would be to work that one out. Yeah. But no, I haven't used observations yet. It was just a first pass, just like having a go at putting the parameterization in. And then we're going to come back and do some observational work in the future.
So you were thinking it's like more in situ or use remote sensing. So what's the data source possible coming from then?
I mean, ideally it would be remote sensing, but I mean, it just depends on what's available. And I think this is going to be the next part of our project.
Okay, thank you.
Yeah.
I think that'll be a good thing to talk about in this session too. Like, what do we use to ground truth waves and ice and stuff like that? All right. Thank you, Green. So our next speaker is Erin Thomas, and she's going to talk to us about waves in E3SM.
Okay. Awesome. So we're going to switch models here, but there is a lot of overlap between the work that I'm doing in E3SM and the CESM model. We're using the same wave component, and we're using IcePack, so the same sea ice thermodynamic column model. But this is going to include a little bit more than just wave ice. It's going to be an overview of the way that waves are coupled into the full Earth system model. And so we'll do a little bit of an overview of how waves are coupled in, what is the recent developments, talk a bit about the mesh that we're using, which is quite different than the CESM, and then some ongoing efforts and future plans. So quick overview. So E3SM is the DOE flagship model. It has an unstructured mesh in most of the components, especially the ocean, the sea ice, and the wave component. You can see an image here. The little blue hexagons is our low resolution ocean and sea ice mesh, with the black triangles being our new wave mesh overlaid on top. We have Antarctic ice shelves and ocean flowing underneath the ice shelves. And really moving forward, the target effort for E3SM is going to be focusing on AI applications and shorter timescales, so more seasonal to decadal prediction. So our current capabilities in E3SM, the new version 3, it's fully coupled, but it also now includes a fully coupled wave component. So we're using WaveWatch 3, just like you all. And we have wave sea ice interactions. So that's my area of interest, but again, we'll focus on an overview of how waves are coupled in to all the other components as well. We, again, are using unstructured meshes, which is nice because it's capable of regional refinement around any areas of interest. Polar regions, for instance, is one of the areas that we often regionally refine. And then for waves, we generally regionally refine around coastlines and shallow regions. And so again, here's our unstructured mesh. This is our low resolution or our standard resolution in version 3. The blue hexagons is the ocean and sea ice mesh, and we're reaching down to 30 kilometers. So this is our low resolution mesh. Again, 30 kilometers throughout the Arctic. And we exactly match in the wave model the mesh resolution along the coastlines. And so here's a bit of a zoomed in version off of Alaska to see what the coastline looks like in both of our meshes. And so we're interested in how waves impact the full climate system. And so we're interested in wave-ice interactions, how waves interact with the ocean through mixing and Stokes drift and Langmuir turbulence, as well as how the waves feed back to the atmosphere through turbulent surface fluxes. And we've included all of these processes in E3SM version 3. So I'll break this down by how waves are coupled to each component separately. But in terms of how waves are coupled to the atmosphere and the ocean, one of the ways that we could view this also is how they are momentum coupled. But I'll just break it down in terms of each component separately. And so the wave atmosphere coupling, in terms of what's physically being passed back and forth, we have winds and temperature being passed from the atmosphere over to the waves, and then roughness length being passed back. And so generally the default version of E3SM, we use an NCAR-based Large and Jaeger surface flex scheme. And there's no way to couple waves in this default setup because the surface drag coefficient is based purely on 10-meter wind speed. And so one of the options that we've experimented with in version 2 was switching to the core turbulent surface flux scheme. This would allow for wave coupling through the Charnot parameter. However, this flux scheme is not consistent with our default setup, which is the NCAR-based scheme. And then also the turbulent fluxes over sea ice surfaces is based on the NCAR scheme as well. So overall, this was not really how we wanted to move forward with wave coupled to the atmosphere. And so what we've done is created a modified NCAR turbulent flux scheme that allows for wave feedbacks by calculating here in the schematic on the bottom. We're passing Z naught, that's the surface roughness, from the wave model up to the atmosphere, where we calculate CDN, so the drag coefficient, the neutral drag coefficient, as a function of Z naught from the wave model itself. And we then iterate through to look for what U star is, so that's the flux calculations there, and then so that affects the tau, so the surface drag on the waves itself. So we've got two-way coupling between the waves and the atmosphere. So moving on to how the waves are coupled to the ocean, we're doing this with boundary layer depth, currents, SST and SSH being passed from the ocean up to the waves. And then the waves are passing back significant wave height, Stokes drift, peak direction and frequency, as well as some stresses. And so that's where this full momentum coupling plays in with the way that the waves are also coupled to the atmosphere. So we'll go with the mixing first. And so we're partitioning the Stokes drift values as calculated in WaveWatch 3, passing those partitioned Stokes drift over to our ocean model. That's called MPass Ocean. We then are reconstructing the full depth profile of the Stokes drift in the ocean, and we use that reconstructed Stokes drift to estimate a Langmuir enhancement factor. In terms of the momentum coupling, and again, this is related to how our waves are coupled to the atmosphere. Again, the default setup with no waves, of course, is that the atmosphere stress is equal to the ocean side stress. But when you have a wave component, this isn't actually true. Some of the momentum imparted on the ocean from the atmosphere is lost to the wave component through the generation of waves. But also the waves themselves can impart a stress on the ocean, and we're now accounting for all of this. And so you can see in terms of the full momentum coupling, it's related to how tau atmosphere is coupled to the waves as well. All right, so maybe a little more relevant for this group is how the waves are coupled to the sea ice. And so we're using, again, WaveWatch 3, same sea ice column physics as CESM uses as well. So we're coupling with wave height and the 1D wave spectrum, and then ice fraction, ice thickness, and the ice flow diameter as calculated from IcePack. And so luckily, I am not the first talker today. So all of this has been presented before. Very nice overview from everyone who's already gone. We're using the IcePack column physics and the flow size distribution included in IcePack. And Letty gave a really nice overview on all of this earlier. The braking scheme is based on the Horvat and Zipperman and Roach et al. Methods. Very exciting to see the new fracture scheme coming out soon, so I'm excited to read that paper. And so sea ice flexes with the height field and breaks if the strain is exceeded. And then the wave attenuation scheme that we're using is based on the Malin et al. 2021, so the same scheme as CESM is using, where wave power is dissipated due to sea ice. All right, so just a quick summary of all the results here. So we've got about 65 years now of the fully coupled wave ice run, but I'm going to break this down into two components. So we ran a control run with no waves. We ran a run where the waves were coupled only to the atmosphere and the ocean. And then we ran a third simulation where the waves were coupled to atmosphere, ocean, and sea ice. So we could isolate the impact on the climate due to the wave ice interactions. But first, before we look at the wave ice impacts, we're going to look at the role on the climate system from the wave ocean atmosphere coupling. And generally, global mixed layer depth increases as we would expect because we've got Stokes and Langmuir effects now. This generally increases or decreases the temperature. So we've got increased mixing leads to cooling. And then this has an impact on the sea ice. Here we're just looking at the northern hemisphere. And the impact of the wave ocean atmosphere coupling is the cooling and mixed layer depth processes generally increases our sea ice area and thickness, although this is just the concentration that we're looking at. And so when we add wave ice interactions on top of all of that, so on the left here, we're looking at what we saw in the previous slide. So this is the wave ocean atmosphere coupling effect minus the control run with no waves. And then on the right-hand side, we're looking at the wave ocean atmosphere ice run minus the wave ocean atmosphere. So we're really isolating just the impact of the wave ice coupling on the full climate system here. And generally the effect that we're seeing is that the wave ice coupling counteracts the impact of the wave ocean coupling, and this would primarily be due through lateral melt. And so the increase in sea ice area that we get through cooling and mixing effects from the atmosphere wave ocean coupling is negated by increased lateral melt through the flow size distribution and wave breaking that we get in the fully coupled system. Here's a quick look at what's going on in the southern hemisphere. And again, we see very similar patterns down here. We see increases in ice due to the wave ocean coupling. And then when you include the wave sea ice interactions, generally it counteracts the impacts of increased sea ice due to wave breaking and the lateral melt. All right, so quickly, some of the ongoing efforts and future plans. Department of Energy is just ever increasing resolution on us. And so here again is our standard E3SM V3 standard resolution in the Arctic. It's roughly 30 kilometers or so. And we're moving towards an even higher resolution where we can't even discern what the grid cells are on the right-hand side there. So in the Arctic, it would be down to more like 6 to 18 kilometers. You can have a guess at the impact on the wave cost if we go there. Also, not just in terms of ocean and CS resolution, we're moving towards a 3-kilometer cloud resolving atmosphere. This is called SCREAM. And because of all this increase in resolution, there's a massive increase in cost. And so AI and machine learning applications are also a really big focus for us moving forward. So here's an example of what we're talking about. And so this is our standard resolution, fully coupled E3SM simulation with waves. And so it turns out waves are almost equal to the cost of every other component combined. And so one of the things we're really trying to do is reduce the cost of WaveWatch. And so we have done some work on this to isolate what part of WaveWatch is really expensive. And so here's sort of a cost tree. It turns out there's only like a few source terms within WaveWatch that take the majority of the cost. And so what we're doing is trying to emulate individual source terms. And so one of our postdocs, Olawale, this paper was just recently published, so I could get you the link if you are interested in reading this in more detail. But what we're doing is emulating the nonlinear wave interactions, which is one of the more expensive terms. There's two ways the WaveWatch simulates this: an approximation, which is what most people use. That's called DIA. But there is an exact term. And so what we try to do is train an emulator on the exact methodology, which is very expensive, to see if we can get the speed of the approximation method. And generally, I won't go too much into detail here. We are successful at that. And so we are getting about the same results in terms of, this is the RMSE of wave height and the peak wave period. And the RMSE is very good for the emulator minus the exact. And so we are getting very close to the approximate, we're getting very good results emulating the exact methodology at the cost of what the approximation methodology takes. And so we're really excited about this. These are all offline results, but we're moving towards online simulation of this as well. And so with that, I will take any questions, and sorry for the very quick overview of all the ways that waves are coupled into E3SM.
We have time for a couple questions.
Nice to see that all these things come together, right? And not surprised that WaveWatch is that costly.
Yes, well, did you see our mesh that we're using? It's very high resolution, and that is very hard to counteract. So we're really looking forward to emulating the wave component.
Yeah, I understand that. The question is, if you do like the successful replacement of the spectral fluxes, like this part you showed last, how much does it bring down the cost?
Good question. I don't have that. The timing would be about the same. So in terms of like, one more, this cost. So this WaveWatch simulation is using the approximation method. And so we wouldn't actually be improving on this. It's about the same. We would get more accurate results. That's the difference. So you're getting more accurate wave simulation through the emulator at the same cost.
Does the accuracy impact your climate responses?
Don't know. We have not run this yet. That's a great question.
I wouldn't guess so.
I don't know.
All right.
Nice to see.
We have a question in the chat, and then I'll go to you, Ed, and then we'll switch. So, Katerini, could you mention which Langmuir enhancement you used? Did it account for wind wave misalignment?
Ooh, that's an excellent question. I did not implement the Langmuir coupling. I will have to get back to you. Could you send me an email? My email is in the top corner, and I will look this up for you.
Yeah, I will. Thank you very much.
Thank you so much. Yeah.
All right. Last question, Ed.
Hi, Ed. Thanks for the great talk. I was pretty fascinated by the results when you couple the waves to the ocean, right? That you got the deeper mixed layers.
Yes.
But you actually got cooling and more sea ice, and I maybe would have expected the opposite. But I wonder if is that a response to the local changes in mixed layer depth in the polar regions, or could it be a remote response to maybe lower global temperatures as the global mixed layer depths are deeper, and that just makes the polar regions colder?
That's a great question. I haven't looked at whether it's a remote or local balance. I will look into that. These results are pretty recent. So yeah, great suggestion. I can't speak to which it is.
Okay, thanks.
We do see generally global changes in the climatology, and I just picked a few of the figures to highlight here for you guys, but there are a lot of changes. So I wouldn't be surprised if there's a remote component to this, as you suggested.
All right. Well, thank you, Erin. So we're going to move to our last talk, which is remote. Noah Day is going to talk to us about the Access OM3 model. And it is almost 4 a.m. in Australia. So thank you for being with us at this time. And you should be able to share your own screen.
Noah went back to sleep.
Sorry, bear with me.
Great. And we can hear you okay in the room. Oh, we're in the infinity mirror.
Yeah, sorry about that. Is my screen coming through now?
Yes, it's not presenter view yet, but I'll let you know if it. There we go. That looks great. Thank you.
Okay, perfect. Hi, everyone. My name's Noah Day. I'm a postdoc at the University of Melbourne, and I guess my research interests are in particularly the marginal icing, which we've had a great introduction to already in this session. So I can probably skip over this slide as you're all familiar, but essentially I'm going to refer to the marginal icing as the area of the sea ice cover where waves are interacting with the sea ice predominantly. So in this diagram, we've got waves coming in from the right-hand side. The sea ice, due to its physical properties, will attenuate that wave energy, and then that results in the sea ice determining the extent of the breakup. So we have this feedback since fractured flows are weaker than continuous flows. So the sea ice and the marginal ice and the waves are intrinsically coupled. So what we're trying to do is represent these processes at still quite a coarse resolution, so at 1 degree horizontal resolution at the moment. There's a project led by Alex Fraser from the University of Tasmania, where we were able to capture Antarctic miswidths derived from satellite altimetry. So we've collected 10 years of data. So this is circumpolar and Antarctic miswidths, where the miswidths defined by the distance in which the waves penetrate the sea ice. In this study, I guess one of the findings of the study was that the seasonal marginal ice zone width, which I'm showing the dark blue here, is both highly correlated with the incoming significant wave height. So that's the significant wave height right at the ice edge, as well as the location of the ice edge. So this led us down the path of trying to, I guess, explain these relationships or the causal chain. So we completed a modeling comparison. So we took those observations and then just compared it to a super simple sea ice model. So this is just standalone Sci6, and then I included a wave ice propagation module, just so we're taking in the bulk wave parameters at the ice edge and then propagating them through the ice cover to enable breakup. With this, despite the oversimplified physics, we were getting really good agreement between both the modeled wave penetration and the observed wave penetration distances. The caveat or the flaw with all of this, though, is since we're using such a simple model, the key processes that we aim to understand still remain very poorly constrained. So to address that, we're developing a three-way couple model between the ocean, sea ice, and the waves. And here it is. Well, it's still very much under development, but Access OM3 is an Australian ocean and sea ice model, with 3 being the third version. So in the past, the Australian Ocean CS models just relied on those two components. And we've introduced WaveWatch 3. So we've got coupling between WaveWatch, SI6, and MOM6. The relevant coupling submodules that I'm interested in are related to the waves and the sea ice predominantly. So as it's been already highlighted in the previous talks, we've got this flow size and thickness distribution, which will take in the wave energy spectrum and then fracture the sea ice. And then WaveWatch 3 will resolve the wave attenuation depending on the mean sea ice properties. So we're also using that Malin 2021 attenuation model at the moment, since that depends on both the thickness and the flow size. But we're also experimenting with a couple other attenuation models. And then for the wave-induced mixing and the Langmuir circulation, we're currently using the KPP mixing scheme in MOM6, and then enabling an enhancement factor to take in the impacts of the waves. So after running that model, are we getting any better agreement with our observations? So here I'm showing the MIS width again. So the observations are in the gray, and then I've overlaid a rolling average. I think it was a 30-day rolling average just to denoise the data a bit. And then the model results in the orange, and here the MIS width in the model is just the distance of ice cover until the significant wave height drops below a specific threshold. But I will mention that although that threshold's kind of arbitrary, our correlations still hold with varying thresholds. So the threshold's kind of determining the magnitude of the MIS width, but we still get this relationship. And we seem to be, getting quite good agreement between the two. For context, using that simpler model that I mentioned earlier, that we were running at 1/4 degree resolution, we got good agreement in the climatology, but we weren't getting as good agreement in the time series. So this has motivated us to complete this analysis. And now we're getting an R-squared of about 0.7, which we're pretty happy with, even though we're at 1 degree resolution. So we don't have too many model grid cells per longitude to resolve these marginal ice emits. So we can further analyze these comparisons between the observations and the modeling by extending both time and space. So there's a lot going on this figure, so I'll go through it quite slowly. On the left-hand side, we've got the climatology from the observation. So we've taken every data point from 2013 to 2023 and then gridded them to create this heat map where we've got the seasons on the y-axis and then the longitudes around Antarctica on the x-axis. I've got the corresponding plot taken from the model output, averaged over the same time period on the right-hand side, and then the line plot on that furthest right column. That's the circumpolar average marginal ice width. So that was basically what I was showing earlier. So firstly, with that, we're still getting good agreement as we were seeing with our standalone SICE models, so that's reassuring. And then the two plots up the top is, so the line plot is the temporal average, so we can see the variations at different longitudes around the Antarctic coastline. And then I've included a map of Antarctica just as a reference point, as we've got some key geographic features around the coast. So I'm just going to step through each of these, I guess, segments bit by bit. So firstly, just looking at the second half of the year. So this is when the sea ice is transitioning from winter to summer. So we're including the sea ice maximum and then the start of the melt season in this time period. And we're seeing really good agreement between the observations and the modeling. So the maximum mist widths tend to be pretty similar. We're getting, I guess, some of these vertical lines, so some persistent narrowing or widening of the mist at certain longitudes. And then that's reflected in our circumpolar average, where the mist widths and the observations are quite similar. Moving to the first half of the year, so from January to June, the marginal assaying is much more variable, and we get quite a lot of areas where the marginal assaying is super narrow, so probably only one model grid cell at this resolution. This is particularly the case on the eastern part of Antarctica, so you can see the strong signal in the model, and that's because there's just so little sea ice around those longitudes that consequently there can't really be a marginal ice zone without any sea ice. The signals in Western Antarctica are much more varied, so we get our annual I guess maximum and minimum occurring at similar times around that region. And then looking at our circumpolar average, we're underestimating the marginal ice zone width at the sea ice minimum in February. And then we're overestimating it during the peak growth season, so heading into May. I'm still disentangling why this might be the case. By looking at sea ice extents for the for Antarctica in our model, we seem to be overall underestimating them compared with remote sensing. Why we've got this bias is still an ongoing problem that we're trying to diagnose. So another thing we can look at is how this breaks down longitudinally. So in the eastern hemisphere, we're generally getting that strong agreement I was mentioning earlier. So there's very little to no marginal ice zone in the summer months, and then it becomes quite wide during the winter. And by averaging over time, we're getting really good agreement in these in these average mist widths for around that coastline. So it seems to be much simpler to model in Eastern Antarctica, whereas in Western Antarctica is much more complex. So our agreement's not nearly as good. And my thinking at the moment is that a lot of this is impacted by the Western Antarctic Peninsula, which is next to the Weddell Sea on the map, and the tip of South America. So I'm thinking as these swell waves are propagating around the Antarctic sea ice, that they've been constricted here and on the western side of the peninsula, that ice is really exposed to wave energy, whereas on the eastern side, it's shielded from that land. So that's why I think we're getting this kind of dark, persistent shading in both our observations and in the model at around maybe 60 degrees west. Just after that point, we then get some of our widest marginal ice zones. So there's the Weddell Sea seems to be super sensitive to waves. And hopefully when we get to quarter degree, we can resolve that area a bit better. So just on what we're working on in the future. So I think just about every talk's mentioned the cost of wave-induced breakup and waves in general. And we're seeing similar things. So from running SICE in standalone, it is costing us about 2 hours of wall time per model year. When we turn on the waves, it's gone up to about 12. I've been experimenting with using some known distributions in place of solving the fracture histograms, and that's really sped up the model. but it does have the trade-off of losing some of that physical detail that we have in the current model. Our WaveWatch 3 component is also really expensive, as Erin mentioned in her talk. So that's been our current bottleneck for moving to a 1/4 degree resolution. Anyway, that's it from me. Thanks everyone for listening. And yeah, if you want to reach out, my email's here.
Do we have 1 or 2 questions for Noah specifically? So I'll do Letty online first. Go ahead, Letty. Maybe we can not quite in the middle, there we are.
You're using for the known histograms, I'm curious. For the way
that was very did you hear it okay now?
Yeah, what am I using for the known histograms?
Yeah.
Yeah. So I've been experimenting with both power law, but I think what might be more realistic is a log normal distribution. So this is kind of going off of Fabien Montiel's work. Yeah, all this work's very preliminary, but I'm playing around with setting the parameters of that distribution to things like the characteristic flow size.
All right, do we have any in the room? If you can stop sharing your screen, Noah, I'll put up
yeah.
topics. And then when I introduced myself, so I'm Alice, I'm the Polar Climate Working Group co-chair. Ed, if you're still online, can you just turn on your camera and wave to people so they know who you are? And then Gustavo, maybe in the room, you can wave so everyone knows. This Gustavo, he's one of the Ocean Model Working Group folks, and maybe Ed's not online anymore. Okay, so
I'm online.
Oh, you are. There he is. So there's Ed, the other Polar Climate Working Group co-chair. So yeah, feel free to email any of us if you have questions about session or anything like that. And Gustavo is coming up here. So we wanted this just to be kind of a discussion period where our communities can talk about kind of things we want to look into, coordinated experiments. I added some things to this slide based on what Letty added in her talk, or things that came up like machine learning emulation came up multiple times. But I was going to have it kind of be an open discussion for the next 20 minutes. Does anyone want to start out?
So I think, so we've seen experiments from other groups that are running with waves, and I think it would be nice maybe to have some coordinated experiments across our groups. I mean, like the experiments that Erin showed with looking at the wave impact, the waves in the ocean, the waves in the sea ice, you know, and kind of piecing apart the different impacts of waves in the climate system. I think those would be nice experiments to run with CESM3, and maybe then we could compare across models and see where there's consistency or not. And I'll throw out another set of simulations that I think would be interesting. I think it would be interesting to see how the waves impact initial value predictability in sea ice. And Ed mentioned, you know, Ed asked the question of, do you see more high frequency variability? And CC said yes. And I'd be interested to see whether that impacts the initial value predictability that is simulated. So coordinated experiments along those lines would be nice too.
Letty?
Kind of just to add on to that, yes, I think coordinated testing for the parameterization development would be really good, maybe just to make sure that we could sort of maybe agree on a bit of a framework so people are doing similar tests and that we're comparing against the same baseline, because things are developing. So I think if we want to show the impact of adding in new processes, that we're kind of doing it relative to the same base state.
Go ahead.
Ed? Go ahead, Ed.
Yes, on that note of coordinated experiments, it seems, you know, like everyone's mentioned how expensive these simulations can be. And so people, you know, are often running kind of shorter simulations, whether it's a few months or a few years. So at least coordinating using the same time period, right? Like if you're forcing it, or maybe if you're running it in like with an observed atmosphere or like observed wind field or waves from wavewatch 3 to use the same time period so that at least you're comparing apples to apples.
You should also then check the switches of WaveWatch itself, right? Because they interact with the attenuation scheme, which is a little messy.
Chris Horvat.
Hey, sorry, I should move you off my second screen. Yeah, I wanted to add that we had a meeting over the summer about wave ice coupled modeling, and we kind of had a plan to set up a set of experiments, but I think as I led that and did nothing with the resulting proposed work, it'd be a good opportunity to kind of revisit the set of plant experiments that we were talking about, especially with the PCWG. So I can't be there today, but obviously would love to hear if there's a plan to do coordinated experiments, especially between DOE and NCAR.
Like the second that we turn on more diagnostics, because I was just looking in the ocean model and I couldn't find anything that really isolated the wave mixing effects other than just the mixer. Maybe I'm missing it, but I'd also be interested in an oceanographer explaining how it's working in MOM, because I used to have a clue in POP, but now with MOM I don't.
So we're saving now, as of maybe a month or so ago, a bunch of ocean wave fields, significant way high, I think peak period, not only things that get passed between the couple, within the coupler, but also additional wave fields. Unfortunately, WaveWatch output is not straightforward, so we had to do via coupler history file, and thanks to Walter for doing that. And then in terms of the feedback on the waves on the mixing, we are saving, within KPP now there is can save the Stokes velocities that are used in KPP. And then the new parameterization that Bill coded up, so it's large 2021. There's 3 kind of components that are coming in. 2 of them are related to waves. There's a lot of details. I don't know all of them. I will touch a bit on my presentation, but we'll write them up in the description paper with the help from Village.
Yeah, making sure in any coordinated experiments that we have them on, some of these fields on, even if they're not default CESM3 fields, partly just because when you run CESM, it has so much output and stuff.
Yeah. Did you say it's in the coupler?
The way we're saving wave field is via coupler history files, but it is a unique file for the wave coupler history files instead of being merged with all of the other stuff. And it's daily snapshots.
Daily averages.
Daily, thank you.
In our standard runs?
Yeah, now is out of the box as of Alpha 07G, I think.
This is more of a question for Aaron. I thought that DOE or E3SM has a rewritten new version of WaveWatch 3.
No. So I guess maybe you're thinking about our sort of longer term plans. Our long-term plans for the ocean component is actually to embed our sea ice component and ocean component and wave component all into one.
No, I'm talking about what Luke was trying to do. I believe Luke was saying that they have rewritten WaveWatch 3.
No, we have not.
You have not? Okay.
Yeah. I would love to, if you want to work together. I'm not sure I'm qualified, frankly, to rewrite a wave model. I'm a coupled modeler, but I very firmly believe WaveWatch is not the right tool for the applications that everyone in this room is trying to use it for. And we desperately need a new climate wave component.
Yeah. I'm going to go to the topic of resolution. I mean, definitely you see improvements in the resolution that Aaron showed, and also NOAA. I mean, running at quarter degree and stuff like that. But the expense of WaveWatch is just so crazy when you go down to those resolutions, and that's why in our standard CSM experiments we're only running WaveWatch at 3 degree resolution. So I love some thoughts, suggestions on a compromised resolution and ways that we can maybe improve the performance of WaveWatch, because I'm sure Dave Lawrence would be very excited if we told him we were going to triple the cost of WaveWatch in the model. So just some ideas and some thoughts on that would be wonderful.
I have a question about the wave spectrum in WaveWatch, because as we go to higher resolutions, at some point, the model probably will not be able to resolve that things so well. So does it make sense to go to such a high resolution?
We are running higher spectral resolution than the CESM component.
Yeah, we've got 25.
I mean, like spatial resolution, but just because I've seen like these wave spectrums, and sometimes they do not improve if you improve spatial resolution.
Oh, okay. Yeah, well,
so for long-term improvement, I have a plan. But I don't know the right model. I still want to do that. For short-term improvement, it's still unclear to me how much of the cost is actually the running of the model itself and the transfer of spectral information to the coupler. And the only reason why this coupler needs spectral information is because of your wave fracture scheme, which is also the expensive part in CSM. So I would recommend stop transferring spectral information and go with the moments and figure out a wave fracture scheme that sits on moments. So
we've tested the cost of coupling, I can't speak for CESM, only for E3SM, and coupling, we couple 36 wave frequencies instead of the 24, 25 that you guys do. It's not that much. It's the wave component itself that's expensive.
Right. Just the state vector of the wave. But the fact that you have so many variables flowing around.
Right.
Okay. Good. Is it the same in CESM? Because when we talked about the performance, there was actually a substantial factor of 10 difference between having spectral things on and off.
Maybe. I'm not sure I looked at those numbers, but again, we're doing 25 frequencies, but we're also running WaveWatch at 3 degree resolution. So maybe the frequency itself is a more significant cost than the 3 degree. But if we go down to higher resolution, then we're gonna, that's all gonna be lost in the noise, I think.
Yeah, I think all tests I've heard of is even if you go to a higher spatial resolution and reduce your spectral resolution, it doesn't help much. Like Greenleaf tried back in the day, and it doesn't really, because at the end you have a 4-dimensional cube you have to get through this computer, right? So, and the way how WaveWatch is structured, it's sadly the way how it is. Yeah.
We'll solve the WaveWatch terrible problem eventually.
Give me funding, then I can.
Well, unfortunately, I haven't found the money tree, but I do. Dan, I saw your hand up a little bit ago.
Yeah, thanks. I wanted to mention the Crocodile project, which we have here, which is really about making regional modeling in CESM much more accessible. So building Python front ends, starting with MOM6. So now we can kind of configure and run regional MOM6 pretty quickly. We're very interested in working with the CICE and CICE communities to include regional CICE capabilities. So right now we can run Pan-Arctic and Pan-Antarctic, but we brought on Dave this year really to develop things actually on the CICE side to enable more open boundary condition capabilities within CICE. So we're hoping so we have these annual workshops. The next one will be in September, October. I'm hoping that we might have some ability to run regional CICE there. And I don't know if you want to talk more about, I think that we were kind of downstream of some other developments within the CICE consortium in terms of these like ghost grid cells on the boundaries and stuff. But we're very interested in collaborating with you all on that.
The one question I have before we continue the conversation is Dan and I have talked about, this September, October workshop, if there's any interest within the more polar community of having a number of polar sea ice people come to this. So if the September, October workshop was a little bit more polar, there was a large group of us, how many people would want to come to that? Just a quick show of hands or think they could come that time of year. 70. Okay.
Yeah. Awesome.
Okay.
Awesome.
Okay. That's good.
And I will just add that Garant was at the, crocodile workshop earlier as well, and had some really cool, regional Antarctic and Baltic Sea results and stuff like that. And we may actually highlight some of that this afternoon.
I know it's hard to plan in general right now, just with life, but
just to add to Dan's point, how much effort is it to do crocodile with WaveWatch?
Yeah, Melissa was just asking this question. In talking to Dave, that's also something that we would love to do. I don't know if it scales with the area of the domain or something like that.
Well, once you cut this down to a region problem around Antarctica, the computation it's way better because you don't resolve the whole globe.
Yeah.
Right, especially in a regular grid setting. So that cuts down the development costs for the parameterizations a lot.
Right. And so if that's a matter of staging, boundary, and initial conditions, we'd also be really interested in doing that.
Historic winds. So it's historic waves. So you can just prescribe the one in WaveWatch.
Cool.
Yeah, I wanted to go back to this. We were talking about intercomparison. And I don't do much with waves. Actually, I mostly try to avoid ice with waves in it if I can. But I'm wondering, do we have the data to back up this comparison? Like, what is the, it's great to compare across the different models, but at some point, if you're trying to make a decision of what parameterization or simplification to go with,
you mean observational data?
Yeah, you need some sort of standard that you're comparing to. And if all the different studies are comparing to different observational products, that would be.
I'm going to say, Chris, I know at your summer workshop you talked about this, so go ahead and speak to it. Yeah.
The answer is we do have some global products. Me, Ed, and Alec actually wrote a paper developing a wave and ice product that Bhutan has used pretty successfully to do WaveWatch 3 coupled comparisons. So on the global scale, that's possible. And there's been some effort to, I think, look at regional information, maybe from Danny Dumont's work in where Canada. So I think there are some standardized data products, but again, it comes down to how you make the comparisons. And Guillaume wrote a paper in Proceedings article or Royal Society article a couple of years ago detailing how to do the global comparison between a couple model and this wave ISAT2 based data product.
Is it a follow-up?
Oh, it's related to this, yeah. So I think ISAT2 has something called freeboard. And so I would really love to be able to put a freeboard estimate into our models to have a more direct comparison to potentially freeboard measurements that come from satellite products. I think that would be a fun way forward to
history file.
Yeah, like something right out of the model. Like instead of calculating thickness or something, have the model estimate what the freeboard is, and maybe we could compare more directly to ISAT2 freeboard. I don't know.
That is a standard CMIP variable now.
Okay.
Yeah, SIFB. I've implemented this in SICE, and it will be part of our standard CMIP contribution.
I guess
we gotta do it too.
So, Khan, is yours on kind of the same topic of output, or is it
Well, go ahead, say, and then I'll.
Well, I was going to say, I just wanted to, either you can say it out loud or come talk to us too, but necessary wave output for CESM or CMIP7. So we brought this up earlier, CC was saying it'd be nice to have more wave fields. Those might not be default in CMIP7, which we think we are contributing to still, just that's the guidance right now, as we haven't been told we cannot. Are the, significant wave height and wave period, are those the two main things we want, or is there anything else that we really need to make sure is output as a standard to understand, and I guess flow perimeter and those sorts of things are default, at least in CESM now. Is there anything else someone wants to put out there that needs to be like standard output in all the models?
I think there's the semi-operated call clip thing that organizes wave-related outputs. Not sure if they care about the CI's components, but there should be synchronization for that. It would be good to have a directional quantity.
Mm-hmm.
Right. So, and it shouldn't be much different than the things we should couple. I think. Right. The stuff you get from the coupler should be a sufficient subscription of the spectrum.
Yeah. I do want to mention that within SICE, freeboard is calculated differently within different parts of the model. And so it's something to keep in mind with any of these comparisons. There's not necessarily like a single value. And there's reasons for that. Yeah.
Going back to the output, I think the paper that Baylor and Patricia just wrote describes the wave fields that are required for CMIP 7.
Okay.
I need to double check, but I remember the correct wave of that.
Okay. And then and I was going to say for development simulations with CESM, like CC said, maybe we can have some other, if we do some coordinated experiments that are coupled runs without wave extraction or with different wave fractures, we can have some extra output from MOM or something, even if that's not a CMIP variable. And we can just kind of get a list of those or something. Okay.
Yeah, so speaking of Baylor, I was going to bring up two things. The paper, that paper is apparently in revisions right now. And if, I think it's available, if you think that there is actually missing fields, I think that can still be incorporated during the revision stage. The second thing is that we had a meeting with him on Tuesday. He was keen on essentially bringing the theory wave model, and which will essentially supposedly eliminate all these costs. But I don't know how applicable that is under all of these things. And he was asking essentially when he can essentially start playing with the theory and Paul, right? Paul with CSM3 versions. So I think, I don't know, I'm just bringing it up because I don't think that anybody mentioned the theory waves, and that can essentially speed up things a lot.
Well, it doesn't propagate. It's a local model.
Yeah, it's probably local, but are there any applicable situations that can be used or not?
Everywhere but the CIs.
And also the latest ocean parameterization relies on the Stokes velocity, which is not available.
Yeah, so there's now the discrepancy to the larger stuff. So there you have to whatever. I'm not that debate, but for the specific problem of wave propagating CS, you have to propagate the wave formation. That's what field waves does not do, right? So Pickles would do it. Otherwise, you have to use spectrum mark. Sorry for the plug. Yeah. So yeah, I think that's. But I think the plan is to have the three models exchangeable, like theory waves and WaveWatch, so that the theory waves runs as a component system in place of WaveWatch. So that's what Paul did, and I think it should be ready to use.
I think it's ready to use. They just want to test it, I think. Yeah.
They tested not in couple, but in G cases. The thing is, our development CSM3 physics it requires fields that are not provided by the theory wave. So we could not go forward with that as is, unless we go back to CSM2 vertical mixing physics, which we don't want to.
Okay, that seems to be another offline discussion.
One thing I wanted to point out, that Gustavo just mentioned G cases. I think we have talked at least offline about having these. So G cases are a fully active ice ocean, but we use atmospheric forcing. So we're interested in having some of these constrained simulations that you mentioned, Letty. So I think those will be something we coordinate on. And then we could use that to compare to, the observed historical period. So something like that will be available that's cheaper than running the whole fully coupled system and stuff.
I'd say it'd be useful to add to that some nudged wind runs, so still fully coupled, but where we nudge the large scale circulation, because then you at least have some coupled interactions with the atmosphere. Yeah. So I think that would be a nice additional set of standard runs. And Ed agreed. He put up his thumb. I know, what a surprise. Someone who's not used these runs at all.
And Letty. Yeah.
One thing that came up was the saving the MIZ directly as an output for CSM. There, maybe Chris has an idea, but because it's a length scale measure, how do you do that? Like, sounds a bit like a Mixler diagnostic that varies on short time scales, but you want to save it as a monthly output. So you need to think about how to actually do that in the model, right? You understand what I mean?
Yeah. Chris, you had your hand up earlier too. I don't know if you.
Oh, that was about something different.
Okay.
I don't have an answer to Mona's claim that I have an answer.
Do you mean like size producing like a hemispheric mean MIZ quantity or something and defined metrics like that?
Yeah, right. So that would be like an online metric calculation, which is unusual, I think, in CSM. But so that you have to program that in the model while it runs, because you probably want like a mean, a max, or a min, or something like that.
Something like that, I would kind of prefer to do offline. So as long as we had daily output, would that be sufficient to get an estimate of the marginalized zone daily or something?
Yeah, that works for CSM probably, but not for CMIP. I don't know.
Yeah.
I was just going to say, with all the discussion about maybe new metrics like an MIC metric or observational comparisons, it'd be good to think about putting some of this stuff into like our standard Cupid diagnostics, which maybe is a longer term goal because we have to get CSM3 finished and all that. But I think it would be nice to have these in the standard diagnostics ultimately.
Yeah. And we'll talk, at least we'll mention Cupid a little bit this afternoon when we're kind of the co-chairs are presenting after lunch. I do want to acknowledge that it's 10:33 and we didn't actually plan a break before this. And so some of you snuck out, but other of you might be like, I need to go. And there should be food and snacks out there. So I would encourage us all to take a break, continue talking out there. And then we'll come back here at 11 for Chris's seminar.
Can we see the comment that just came up?
Yeah.
It was something about, I think, modernizing WaveWatch 3 maybe?
Yeah, I think Hendrik has some plans. Yeah. But what's the time frame for that, Nick?
I don't know that exactly. But if there's things to work in, they can be worked in. I think that's worth noting.
Great. We will see you back in here.
The ice sticks up.
I think we're gonna get started in just a minute here. Okay, so we're gonna go ahead and get started. So most of this afternoon the first part of this afternoon is going to be CESM3 development overview and component status. And then I presented this morning. So we're together from about now until 3 p.m. and then there's a break. And then at 3:15, the Polar Climate Working Group is going to meet in the Damon Room. So at the end, at 3 p.m., when it's break time, if you don't know where the Damon Room is, find me or Dave and we will show you where to go. Otherwise, if you're Ocean Model Working Group, you're going to stay in this room. So you don't have to go find anywhere else. And that's when we start splitting. And then at 4:30 p.m., there's an optional self-pay gathering at Southern Sun. Bring cash if you're going to come. Southern Sun is down the hill. Again, if you don't know where that is, come find me or Dave or Gustavo or Ian. Before we start the component overview, we're going to have a presentation, kind of an ad for a June workshop cross-working group session that Diamond Takara is going to present. I don't know that she's here yet, but I also wanted to say I already introduced myself to everyone this morning. Ian is here now, so do you want to stand up and at least wave to people? Ian, in case you don't know Ian, this is Ian. He's one of the Ocean Model Working Group co-chairs, and then Gustavo, who already waved his hand. And Ed should be joining us online, and he's the other co-chair for the Polar Climate Working Group. Do we have Diamond online? I had a thing before, but I don't see it now.
Just one quick thing. Southern Sun does have an ATM.
Oh,
so
thanks.
You can get cash there too if you don't have.
I don't see Diamond online yet. Well, I guess it's 1 minute away, but cancel, sorry. I'll share this, and if Diamond comes, then she can add some context to this. But so in June at the big CESM workshop, there's going to be a cross-working group session about storytelling to craft climate science tools for communities. And this is put together by Laura Landrum, who many of you guys probably know, Mari Tai, Diamond, and then James Doney. Is that how you pronounce his last name? Doney. So Joan, okay. It is, yep, you could just say done. I'm sorry. So we would encourage people to be part of that if they're interested. Go ahead.
Diamond's face was on the.
Oh, she was for a second?
Slideshow. You see?
No.
Live there. You see. Yeah, but you could just have the tab version. That's true.
I guess, Diamond, if you're able to share your screen with this, let me know. Otherwise, I can share. I'm just not seeing her on the list of people in the room. I see that she is has it open, but she's not in the meeting at the moment. So maybe what makes sense, I'll start with just kind of where CESM is in general. We'll check in if she's here before we get into the polar sea ice status, and then we'll do that, and I bet she'll be here by then, and then we'll do that, and then the ocean model status. So without further ado, oh, sorry. Okay, so CSM3 development and overview and component status. So some of this you guys will probably be like, oh, we already know this. Why are you telling us this again? So the first thing we wanted to announce, just so everyone is aware, we are still planning on a CESM tutorial this summer. The application is up right now, and the deadline is next Tuesday, the Tuesday after that, February 17th. So if you or your students or postdocs or whoever is interested, please apply. There's no cost to attend, and we are hoping that there will be travel support available. I think there's a lot of uncertainty around that right now. So if in doubt, I would say apply and then ask us, and Elizabeth Faircloth will organize that, and she'll have a lot more information. All right, so CESM3 overview. This is from Dave Lawrence, just some overview slides. So there have been significant updates to all of the component models in CESM3. Obviously, you're here because you're probably interested in sea ice or ocean parts, but you can see surface waves as part of this here as well. And then big changes to the land ice, the land, and the atmosphere. And if you want the full list, this will be posted of what the changes are and why. There's information here with links. If any of you are interested, we just want to make sure everyone's aware of this. On GitHub, there's a development run database, and we track all of the development simulations. So again, you can click this link when you get the slides. And this is kind of what the GitHub page looks like. And they have information in here about the simulations, what's different about them, links to the case directories, links to diagnostics if we have those, and any other discussion. And what that looks like is if you click on issues, that is about a single simulation. So when we talk about 271 later or something like that, that's case number 271. If you click on here, you can go look at what that is about. And then there's a discussion if there's a bigger issue. So you'll learn about the Antarctic circumpolar current. There's a discussion about what's going on with that under the discussions. And then the timeline. So this is, a while ago. CESM2 release was in June 2018. It was an 8-year development timeline, and we had 299 configurations. And we are almost there, and we're pretty close to this, where we have been working on this since 2018. And I think it really will be released soon. And we have just over 300 configurations. So I think we really are almost there. The target release date is June of this year. I think we are likely to, what Dave Lawrence said is we're likely to have some pre-industrial control simulations by the June meeting. I don't know that they'll be done. Just so everyone's aware, we are planning to do the CMIP7 DEX simulation still. We haven't been told that we can't, and we feel like this is important for validating and showing that our model is skillful and reasonable. So that's what these simulations are with the deck. So like I said, it's necessary for model validation and assessment. We are planning to do some other simulations if we have sufficient resources to do so, some of the other MIPS maybe, but we haven't decided which MIPS, which scenarios, all of that. And we would welcome your input during the discussion if you have strong feelings about, a different scenario you want or something like that. And it will all be resource dependent, of course. I don't know why that came back in later. And then some of the things you'll learn about today, things that have been slowing us down, because you probably thought, well, it's been several years. So there have been challenges with the ENSO. I didn't add as a bullet point. There's been challenges with the Amazon and that it's too dry. And I think all the plants die. So that's a tree falling on someone. The Labrador sea freeze has continued to be a challenge, though I think we may have a permanent solution that we'll talk about, or hopefully permanent solution. And then most recently, we've been running into some challenges with the Antarctic Circumpolar Current, or the ACC, that the ocean model folks are going to talk about. So we're working on these actively, but I think we're kind of whittled down to some of the last few things that we need to address. And then there was a atmospheric model working group talk by Isla this Monday, if you wanted to look at that, about ENSO. We're going to talk about the lab sea freeze, and the ocean model group's going to talk about the ACC. So let me check if Diamond is online now. Do you see her online at all? No. Okay. I guess given that we don't have the presenter for this, I'm going to just say that since I'm not one of the people putting together this cross-working group, look out for more information about this cross-working group session about storytelling. And part of the point is to better communicate our science to different communities, make it more accessible, stuff like that. If Diamond comes back later, maybe we can hop off and talk about this. But in the meantime, I think we'll talk a little bit about the sea ice model and where it's at, and then we'll go to the ocean model. Okay. All right, so the sea ice model status. So again, some of this stuff you've probably heard before. What's new in SICE in CESM3? So the two big things are the flow size distribution. And if you were here this morning, you heard all about flows and sea ice and waves in the ocean. But we also have a new melt pond parameterization that's one of the more significant changes. The biggest challenge I would say has been, we had some challenges with the flow size distribution and cost, but the lab C was one of the other challenges that we think we have hopefully solved. And what we're going to show here are two simulations. So like development run 271 and 287, which are some of the 271's the longest run we have right now, though it has known issues that has a pretty close to final-ish configuration. And 287 is one of the test runs with some changes in the ocean. And the diagnostics, you can look at these if you look at this, if you click this link when you get the slides. And one thing we wanted to mention is these are part of the Cupid package. And we're interested in, if people want to add diagnostics to this, we're happy to work with folks to get those included. I think Marika mentioned this earlier, like maybe marginal ice zone area is something that we'd want to include in the future. All right, so here's our timeline. In CESM3, right now we have this flow size distribution, or the FSD. We have the sea level melt ponds. David Clemensoul, who is somewhere in the room, you moved slightly, so I didn't know where to find you. He primarily led development of that. And then we have some advanced snow physics, but I want to emphasize we don't have all of that on. We only have the wind redistribution component of these snow physics on. So all of these are in the fully coupled system as default. So if you run it, they'll all be on. So I would say the CSM3 code is mostly frozen. It's just model tuning and finalization and like dealing with issues that's ongoing. There's no major other things going into it. And we're hoping to have these pre-industrial runs by June, or at least started by then. And then what Polar Climate Working Group's thinking of for beyond CESM3, you've probably heard, again, some of these before, but landfast ice with a sub-grid scale bathymetry. We have parts of this in, but we didn't have it fully working by the time the code freeze happened. A size 6 MOM6 coupling on the C grid. Again, I've done some work on this, ran into some issues, decided to put more energy towards getting the flow size distribution in the model. We're getting some improvements to ice conduction that will be in a later version of CESM3, as well as congelation growth. On the wish list, feels like perpetually, we have sea ice biogeochemistry. So that top group is like very likely to be in a relatively soon release of CESM3. Sea ice biogeochemistry, I had been recommended for funding for this from NOAA, but now that funding is on perpetual uncertainty. So maybe it'll come through, maybe not, but we really would like to get the sea ice biogeochemistry coupled with the marine biogeochemistry, and maybe do some other polar improvements to it. And then ice radiative transfer. And then things that have kind of popped up in the last years is things many people are interested in is working on machine learning and some of the machine learning parameterizations that'll go into a machine learning enabled version of CESM3. Specifically with the flow size distribution, though if other people have other machine learning things they're doing, we'd love to hear about that. And then interest in regional ice ocean wave modeling. All right, so this is part of the regional ice ocean wave modeling. There was a workshop back in October. Dave Bailey attended, some of the other people in this room attended, and people were successful at setting up some of these regional grids with sea ice. And, but I think there's still some ongoing questions like how you deal with boundaries, how you deal with waves that's not in the regional models, potentially biogeochemistry. So there's lots that we're interested in. And in the morning session, Dan brought up, you know, there's likely to be another workshop, and many of the people here said they were interested in attending one of these crocodile workshops that might focus more on polar things, or there would be a big group of us from polar that would attend. So just pointing that out, if you're interested in this or you want to be involved in the development, we're excited to have you. All right, so just a little bit about the FSD. We heard about this all morning, but some of the people have changed in and out. So in CESM2, what we had was a constant flow diameter of 300 meters. The ocean waves were not damped at all by sea ice, and the ocean mixing was not impacted by waves or anything like that. In CESM3, we now have a prognostic joint flow size and ice thickness distribution. So you can see in this schematic, the flow sizes are different. There's also ice thicknesses within there. And the waves, the ocean waves are damped by sea ice. So this will damp the waves, and then it will impact ocean mixing below the sea ice. So we do have one-way coupling to the ocean. If you were here, Aaron talks about coupling to the atmosphere. We don't have anything like that with waves. And this is really important when we get to the Lab C situation, because what happens is when the waves break the sea ice, we get more lateral melt, which can lead to more open water, which can lead to more waves in some of these areas. And that's really what helped us, we think, deal with the Lab C freezing over issues. The second main parameterization we're going to highlight is the sea level melt ponds. As I said, talk to David if you want all of the details, but I just tried to summarize it here. So in CESM2, we had level ponds. The ponds, IPO ponds sit on top of the sea ice. They are sit, whatever. The area and depth grow by fixed ratio, but when they drain, it only reduces depth. So we had way too extensive melt ponds. This kind of nicely canceled itself out in that we ended up getting a really good albedo because we had compensating biases, but the melt ponds were too extensive and too shallow. David's done a lot with these sea level ponds where we actually account for sea level. When they drain, you reduce both depth and area. And this is based on the elevation above sea level, which is the hypsometry. And I'm going to point you to David for any other questions you have about it for lack of time here. All right, so S, probably many of you know, the Labrador Sea freeze has been a long time challenge in CESM. And so this is back from CESM2. I actually remember some of this vividly because I had my second daughter. It was like, everything's fixed. And then the last run I looked at before she was born, it froze over again. And I was like, not my problem. And I came back, it was still a problem. So where you have that box right there, that's showing the Labrador Sea. We get ice that grows out far too far south and east. And these are cute things. This is a slide I got from Cecile. So Cecile is saying we're trying to figure out how to drag the CESM boat over this ice. So this issue has come up over time in CESM, and it reemerged in CESM 3. So the problem was basically related to too much fresh water in the Labrador Sea. The thing that was really challenging about it, as you can see from this plot, is sometimes the Lab Sea froze. That's what happens when these ice fractions jump up. It would happen right away, but other times it happened after like 200 years. So you'd think you were good, and then you weren't. So it was really unpredictable. The Lab Sea would freeze in like 30% of the runs, but in the other 70%, it was like, well, it's not frozen yet, but who knows what's going to happen. And once it got frozen, it would stay frozen. And the thing that seemed to really, the two things that kind of impact this that we've used to address it are, first, we turned on the flow size distribution, and that has to be fully coupled. So we're not just passing wave information, ice information to the waves, but that the flows actually evolve over time. And we have turned off the Bodner ocean parameterization in the Lab Sea. And I'll try to explain that. And if you're an oceanographer, I'm sorry if I don't get that right. But this was, I think, the first case 247 where I think on a hunch, Dave kept the simulation running and it froze and then it unfroze. And we were like, well, is this a weird one-off? And nope, in fact, this is what happens consistently in these simulations where we have the flow size distribution on. So the Lab Sea will freeze and then you break up, the waves break up the ice and you get that feedback starting. And then it seems that that is able to lead to an unfreeze of the situation. Unfortunately, we can't turn Bodner on. That is not a solution. So here's the feedback I just explained. That is how we are dealing with the Lab Sea. But for Bodner, so what Bodner does, it's a mixed layer eddy scheme. It basically deals with restratifying the ocean mixed layer, and it opposes deep mixing or convection, which is something that happens in the Lab Sea. And when the mixed layer depths get really big, restratification increases. So when this was on in the Lab Sea, it would basically restratify the Lab Sea. That would suppress convection. Heat doesn't get up to the surface. It's cold and it would freeze, and then we couldn't get out of it. And we did try a number of tests where we'd turn it on with various parameter values and other things, and unfortunately none of them were successful. So I think the final decision is that this will stay off in the Lab Sea. The oceanographers can correct me after if I'm wrong. All right, so Dave's going to talk about the current status and how sea ice looks in the development simulations. I think go ahead.
Sure. So apparently this is me, the inquisitive penguin. So I guess we put together some diagnostics using the Cupid package, which you've heard a bit about. And I think we'll maybe go into a bit more detail about what it is tomorrow. But it's basically the CSM unified post-processing and diagnostic package. It's replacing what we had before for CSM2. And it's still under development. So we're definitely looking for feedback on different things that we would like to include in it. So as Alice said, 271 is the longest simulation that we've got so far. But it, the oceanographers will talk more about some of the issues with the Antarctic circumpolar current. And then 287 is sort of almost our best tuning. I'm sure that there's still more to come, but at least for now, this is kind of where we would like things to be. And then, yeah, the atmosphere is still working on tuning some things, trying to make sure that they get the ENSO they want and so forth. And so while our development, our piece of this is done, we may still have some tuning to do. So, and this is just sort of saying more about the Cupid package. There's a web link here that you can follow. It's fairly well documented now. We haven't really tested portability to other machines yet, but it does work on the NCAR machines very well. And we would definitely like other people to start helping and contributing to this package. So 287 versus 271, in terms of like a lot of the, standard metrics, it actually looks like these two runs are fairly close together. sure. Yeah, there's my mouse there. You see the Northern Hemisphere sort of climatological seasonal cycle near the end of the runs in each, and you can barely tell the difference between the blue and the red curve. They're very, very similar. I've put on here the black curve, which is the CDR, which we heard about this morning. That's present day, of course, and these are pre-industrial runs. So we would expect that we should be above that somewhat. And so that when we go through the 20th century, we're going to expect some melt back on that. And then we have some fairly nice statistics of comparing the different runs in these box plots to sort of get an idea of the spread in the runs over time and how they compare with the CSM1 and CSM2 large ensembles. The CSM1 large ensembles in gray here and the CSM2 large ensembles in blue. And then here with volume, again, the two CSM3 development runs are not really that distinguishable in terms of Arctic volume in the seasonal cycle. You can see we're at kind of the higher end of the CSM1 large ensemble in terms of volume. But so far, with the historical runs we've done, we're not that concerned about it yet. But I think we definitely feel like we should be within the sort of CSM1 spread instead of CSM2. CSM2 was too thin in present day, so it's kind of desirable to be closer to the CSM1 large ensemble. And then, some additional plots that we have, we can look at the whole run length. And so this is on the left here, we have the annual mean ice area. And you can see generally, there's slight variability differences between these runs over time, but in general, they look pretty good. And the reason you're seeing the CSM1 and 2 large ensembles sort of drop off is because they're historical runs. And so you should only really think about the early part of that period there. And then we have some spatial plots too, to look at some of these things. So sea ice concentration, I've got on here in the pink line, the 15% contour. And so as CC pointed out this morning, these runs are actually looking pretty good in terms of the Arctic extent and concentration, maybe a bit thick in terms of the thickness, but that's another thing. And then in terms of the volume, again, they were very similar, but you can see a lot larger variability in the volume. This may actually be related to some of the variations that we're seeing in the ocean too, although this is Northern Hemisphere, it's kind of more obvious in the Southern Hemisphere. But in general, the thickness pattern is kind of what we're expecting when we're getting the thickest ice over towards Canada and Greenland. And then we also have snow volume as well in these plots. And so what's kind of interesting here is that CSM1 large ensemble had a very high snow volume in the Northern Hemisphere. And that also, it tended to create a slightly colder climate, especially in present day, whereas the snow volume significantly reduced in these new sensitivity runs. So that's interesting in itself. The reasons why we're not sure yet, it may be less precipitation from the atmospheric model, and it may just be differences in processes within the ice as well. Then also, as Alice highlighted, we do have wind redistribution of the snow, and that may also be contributing to this too. So then we also have tons of different metrics for different things. I've included flow size perimeter here as that's one of the key metrics that we're looking at when we're trying to think of either the machine learning method for computing this or the full flow size distribution, because this goes into the lateral melt. And you can see here, the Central Arctic flow perimeters are very, very small. And that's because it's much bigger flows. There's less perimeter around the bigger flows. And then out near the edges, what's kind of interesting to me in these simulations, and maybe Letty or someone else can explain this, but there's this kind of peak in the flow perimeter right sort of just before you get out to the outer ice edge, and then it drops again. So I'm kind of interested in what's going on with that process. The ice velocity plots, I will apologize. I'm still kind of struggling with these in Matplotlib, so would love to talk to anyone who's got experience with the quiver plots, because it's very, very difficult to get these. You know, the old NCAR command language NCL did a beautiful job with these, and so I'm having a little struggle here. But that is part of our diagnostics. And then we're underneath the vectors, we're just contouring the speed. And so you can see this white area off the coast of Greenland where the velocities are just flying along. Let's see, Southern Hemisphere. This is where we see a little bit of more of a difference between the two simulations. And I think overall the seasonal cycle is fairly comparable and pretty good. We are worried a bit because we're really low in summer. So the black line here, which you can barely see, is the present day OBS for the Southern Hemisphere, and we're below that. So in a pre-industrial context. So the only problem is we don't know how to fix that in the summer. So thoughts on that would be great too. In the winter, we're a little bit higher than the OBS. So, you know, and that's okay. It's a pre-industrial run. And so the idea is over the 20th century, we would expect some decline in that. However, I will say, I think we have the time series. You know, there's a lot of variability in the Southern Hemisphere sea ice too. So we're just, that climatological plot was over 30 years. And so I think what we're just seeing here is Southern Ocean variability. You can see here the 287 run, near the end of it, it kind of pops up, you know, differently. And some of this variability is probably related to the Antarctic circumpolar current as well. And you can see this similar sort of thing in the ice volume and the snow volume too, that variability over different, you know, multi-decadal variability and so forth. And there's a little hint of this sort of oscillation going on here, though it's not as obvious in the annual mean plots. And then similarly, we have flow size perimeter, ice velocity for the Southern Hemisphere. Same sort of thing, the flow size perimeter, we're getting, you know, larger values in the interior of the pack, and then smaller perimeters near the outside of the pack. So, and all the major features we're expecting in the velocity plots are, you know, we're getting that sort of related to the ACC transport. We're getting that same sort of transport in the ice as well. So I think that's it. We'll hand it over to the oceanographers now.
Diamond is online now, so we're going to have her just quickly present, and then we'll hand it over to the oceanographers. All right. Are you able to share your screen, Diamond?
Yeah, well,
I can do it too, and we can hear you.
Oh, okay. Yeah, if you don't mind doing it for me, just so that I don't want to take up too much of your time. The authors of this EOS article that I'll throw in the chat, Laura, Mari, myself, and James, and Julie Maldonado from Lycan, we wrote this article in EOS that came out a couple months ago. The title of our EOS article is Environmental Hazard Impact Metrics That Matter. Basically just trying to make a pitch to our scientific community that, you know, our disciplines and the way that we communicate our science to each other is very limiting, where we don't reach broader audiences. We don't reach communities, people who live in these areas that we do our science in. And so our CESM workshop cross-working group session is called Storytelling to Craft Climate Science Tools for Communities. just wanted to throw out to everyone, if you could keep an eye out for this session and please join us if you can. Basically that's it. We just want to keep having this conversation with our fellow scientists and trying to figure out how we can reach more people who will be and are currently impacted by the science that we do. So these are just different iterations of slides that we were trying to put together to engage you folks. So yeah.
All right. Thank you, Diamond.
Thanks, Alice. I'm so sorry.
Happens.
Thank you.
Okay, now moving to the CSM3 ocean model status. I think we're running out, we're kind of behind the schedule, but we have discussion after, so it's okay that we take our time here. Since Alice mentioned that there were over 300 couple runs so far, I decided to also throw how many ocean-only runs we have done in 2025 alone, and it was almost one every other day, so it was 159. There's actually more because Ian likes to do A, B, C, G. I think it was way more than 159. So this table is summarizing the key differences between our old model, POP2, and then the GFGL MOM6 version and the CSM3 MOM6 version. I'm not going to go through all the details. It will be in the slides that will be shared with everyone for your reference later. What we will touch upon today are what's highlighted in blue. So these are kind of major changes that were done over the last year. So there's changes with APP and the FPMix and Stokes-Most package, and then the adoption of the Bodmer scheme, as Alice already indicated, with wave coupling, which is new. I'll mention briefly. And then there's the two backscatter schemes that Ian have developed, and Ian will talk about these two as well. Okay, before we jump into the physics changes, as I was preparing this talk, I decided to look at 287, our best fully coupled simulation. And then I compared against the GKs, just in terms, not just to make the point that we have too much precipitation in the couple runs. I've shown these type of plots in the project meetings before, but I want to highlight to the broader community. So we're looking now globally, like if you integrate globally all the river runoff in the GKs in red versus, which is coming from the GRA, versus the fully coupled 286, that's the discrepancy that we see. So this is liquid runoff. Here is frozen runoff. And then in the couple run, we're separating the frozen runoff coming from land versus the frozen runoff coming from the glacier model GLC. Okay, so if you take a look at these numbers, and there's 40% more liquid runoff in the couple model globally, and 80% more frozen runoff compared to the GRA. So that we do a pretty good job at constraining Raston, but the hydrological cycle is very different between G and B cases. Of course, we're doing salinity restoring in the G cases, so it doesn't play a role, but it's interesting to see, and I think we should try to understand what's going on and have the two type of runs be more similar in terms of the P minus E budget. If I was looking globally, you can also look at the lab C only, the same type of thing, and it's 24 more liquid runoff in couple runs and 500% more frozen runoff. And remember, frozen runoff, when we add in the ocean, there's latent heat associated with melting that. So it's not just the mass addition, there's a big contribution in the heat budget as well. So no wonder why our lab C freezes pretty quickly in these fully coupled cases. And then finally, this similar issue in the Southern Ocean, although it's not as bad because they balance each other. So there's way more liquid runoff in forced runs, so 500% more, which is constant, by the way. Both the frozen and liquid in the G cases are constant around Antarctica. But then we have 100% more frozen runoff. And if you look at the numbers, it kind of balances out. So they combined are not that bad. The issue might be here how we spread them. And I think if we have time, we will talk a little bit about that now towards the end of this talk. Moving to the parameterizations. So we already mentioned that we adopted the Bodmer 2023 MLE formulation. And before we were using the FFH, so the Ferrari, it's Fox Amper, Ferrari, Hallberg 2010, I think. So that was using CSM2. It was using earlier versions of CSM3. And that parameterization, so the stream function on the left here is the old parameterization, the FFH. On the denominator, you have the L sub F parameter. So that is the length scale of the fronts in these mixed layer eddies. And that was prescribed. And you also had that C sub E constant. So there's like two tuning knobs that you had to prescribe. And you're using the same length for the frontal length scale globally. And Bodmer improves upon that by it's better physics. And then with that, you remove the need to prescribe the length scale, and that's kind of done prognostically for you. So it is, there's a lot of advantages in going into that scheme. So I mentioned the frontal length scale, but also in the paper, they provided a way to couple with the waves, even though that's not what was done initially in MOM6, but then Bill Large and we added the option to enhance the U star that goes in the denominator by using the Langmuir number from the wave model. So there is now a coupling with the wave model going into the MLE as well. So good reasons for switching to these Bodmer 23 schemes. And then we mentioned the lab C freeze issue. And if you look at the stream functional, we can focus on the one on the right-hand side. There is the lowercase h, so that's the boundary layer depth. There's the capital case H, which is the mixed layer depth, both of which are very deep in the Labrador Sea. So you will generate circulation. And also we have, as I mentioned, we have this bias in the precipitation, therefore the runoff. So we have very large gradient of buoyancies in polar regions in general. So therefore you're also enhancing the circulation by that. So because of that, like deep mixed layer depths, deep boundary depths, and large gradients, the restratification in the Labrador Sea is very strong, and that it's opposing convection and therefore is leading to the lab sea freeze. And to give you more of an idea of how that we've been trying to understand that, so we focusing on again on the Bodmer, so the right hand side of the stream function. We can set this constant CR, which is the only knob that we have here, to 0. And here is in the couple case, how the stream function looks like. So basically, only in the Labrador Sea, by the way, there's 0 effect of this formulation, this parameterization. Then elsewhere in the globe, in that case where CR is equal 0, CR is 0.01. But then we decided to, let's use the same CR and now turn on in the Labrador Sea. And then you see this circulation. So it is converging in the middle of the Labrador Sea. So it's bringing fresh water into the middle of the Labrador Sea, and that's shutting off convection. But then we'll say, what if we have that? And at least we can try to keep the Bodmer on everywhere. And having CR doesn't really have the string function. There's a lot of nonlinearities going on. And I think because of this gradient in buoyancy, so the string function changes, but the magnitude is still strong enough. So we've reached the point that even a very small amount of submeso through Bodmer in the Labrador Sea, it is leading to freezing. If I do the same exercise on the G case, forced case, it's completely different. I can see a better response on the string function to the CR, but in the couple case, things go pretty wild. And then the two cases that CR is non-zero, they lead to lab sea freeze, and that's shown in this time series of area integrated mixed layer depth in the Labrador Sea only. And you see the freezing in the red and blue time series. Okay, so that's just what I said. So then we're very kind of constrained, we cannot turn on this parameterization in the Labrador Sea, otherwise we'll lead to freezing. Okay, so now moving on to KPP. There were a lot of changes to KPP. So we added the explicit effects of surface waves, Langmuir turbulence. And by doing that, we had to remove the implicit wave effect. So if you go into CSM2, there's an assumption of what the waves are doing, hard-coded into the KPP. So when we explicitly added the waves, we had to remove this implicit wave effect. And then we had to rebalance by compensating errors. And then we also added this cross-graded non-local momentum flux. It's called the FP mix. And both of these topics were covered by Bill Lart's 2024 OMWG talk. I put a link here. And he is the best person to describe these things. However, over the last year, we made a change into how the boundary layer calculation occurs. So before, the original KPP uses the Richardson number-based method to estimate the boundary layer depth. And then we had some pretty large biases in the equatorial thermocline. And then Bill decided to try a energy-based or the entrainment rule depth of his 2021 paper in conjunction with the original KPP Richardson number-based. So it will use the entrainment rule if the surface non-local buoyancy flux is negative. Otherwise, we'll use the old Richardson number-based. So that's what we have right now. And just to give you a sense of how that improved the model, here is using the old method for boundary depth calculations. So we're looking at temperature bias at 75 meters and focus on the equatorial regions. You have a very large bias in temperature. So this is a model minus the World Ocean Atlas. And then when we switch to the new method, which combines both entrainment rule and Richardson number, we were able to improve the equatorial part in particular. There were some detrimentals elsewhere, but clearly improves the equatorial part significantly. So that was the key factor for deciding to go to this combined way of computing boundary layer depth. Okay, now I'll hand it to Ian. He will talk through the rest of the changes.
All right, thanks, Gustavo. Yeah, I'll just use the mouse. So a few other things we've added in the last year. One of them is this stochastic backscatter scheme called GME. GME was a scheme that Scott Bachman developed when he was here, and then I came along afterwards and made it stochastic. The idea is that the Jen-McWilliams parameterization removes potential energy from the resolved scales by slumping isopignals. It moves light water over dense water. And that energy that's removed sort of goes away. I mean, it goes into a subgrid scale energy budget, but theoretically, some of that should probably get converted to kinetic energy and go back into the model's resolved velocity field. So the backscatter scheme here takes some fraction of this energy that's removed by GM and puts it back into kinetic energy. And it has several effects. The main effect, which was the intended effect, was to improve the variability. So I've got sea surface temperature, standard deviation, temporal standard deviation up here from a daily observational product. And this was the bias in that quantity without the backscatter. And then on the right, these are just different tunings of the backscatter. This is the change in the simulation with backscatter compared to the control. So we want the colors to be opposite. And indeed they are in most of the places. They are reducing the bias. They don't remove it fully. We're still deficient in variability, but they are significantly improving that. One of the things, so that's in a G case on the right. When we tried this in a B case, a coupled case this summer, it had a big impact on the Southern Hemisphere sea ice area. And it improved a bias there. So the blue run does not have this backscatter and the red run does. Brought the area down, and the ICE team liked that, so we decided to keep it on. That's one of the backscatters. There's another backscatter that is turned on in the model, and it is, I have actually a talk about it at 350 in the ocean model group, so I'll say more about it later today. It is a different kind of backscatter. It represents a different process. We have a biharmonic momentum mixing, a biharmonic viscosity in the model that removes energy, and that's unphysical. So this backscatter scheme puts some of that energy back in, the energy that's removed by the biharmonic viscosity. And it does it in a different way. It's not stochastic. And it just so happens that these two backscatter schemes tend to operate in different parts of the ocean. This one is acting mainly in the tropics. The other one on the previous slide is mainly acting in the extratropics. And one of the big effects of this scheme is in the zonal flow in the tropics, in particular in the Pacific. So I've got here a meridional section of zonal flow. This is observations. This is CESM2, CESM3 without the backscatter, and CESM3 with the backscatter. You've got the equatorial undercurrent is kind of the blob in the middle. And here in the OBS, you can see there's a deep countercurrent. And then on the flanks, north and south of the equator, you get these jets, which have various names, including Tsuchiya jets, named after one of the people that first observed them. And in old CESM2, CESM3 without backscatter, you don't see those things, but you do when you turn on the backscatter. And as was pointed out by Keith Lindsay when we first saw this, this could have an effect on the ocean biogeochemistry, and in fact it does. It reduces a bias in the extent of the oxygen minimum zones in the eastern tropical Pacific, which has knock-on effects on other aspects of the biogeochemistry. So this is, the blue line here is RMSE in one of the nitrate. And without the backscatter, it's quite high, and with the backscatter, it goes way down. Same thing with oxygen, not as big of a change, but still an improvement. So that is currently on by default. There are some detrimental side effects of this, which I'll talk about in my talk this afternoon. So how does the equatorial undercurrent look in our current configuration? Here's observations. So this is a zonal section now across the equator of zonal flow. You see the equatorial undercurrent here, a little bit sloping. This is our current development run. You can see we're a little bit too fat vertically, and we extend maybe a little bit too far to the west. We have here CESM2 results on a different color scale, but the conclusion is actually they're kind of similar. So the equatorial undercurrent in CESM2 and our current CESM3 are pretty similar. Okay. We're currently dealing with a problem with the Antarctic circumpolar current, which was alluded to previously. So here I'm showing time series of, Gustavo made this plot. I'm just talking about it. We're showing time series of the transport through Drake Passage, volume transport. 271 is this long run. And you can see the transport starts in the, where am I going here? Transport starts in the gray, which is the sort of observational range, and then it drops way, way down, 110 sphere drops, which is way too low. And then it recovers, goes back up, and then it goes way back down on a very slow time scale. And we were not expecting to see this. So we tried tuning a lot of things. This spaghetti is all just different tunings that we've tried. Our best one is this line here, the kind of light gray line, that's 287. We are doing some more tuning ongoing, hoping to improve this further. It does seem to be associated with convection, deep convection in the Ross and Weddell seas, and in particular, a lack of deep convection in the Ross and Weddell seas. So in those seas, the stratification with respect to temperature is inverted, so it's warmer at depth and colder at the surface. The density stratification is dominated by salinity. That's why the warm anomalies don't just rise up on their own, because it's warm and salty at depth. And if there's no deep convection to release those heat anomalies, they just build up, and then the temperature gradient and thus the density gradient meridionally across the ACC decays. You get less of a density gradient and therefore less transport through geostrophy. And so when these anomalies at depth build up, the ACC goes down. When a deep convection event wipes out the anomaly, the ACC recovers, and that's giving us some insight, and we have some hypotheses as to how to fix this, but that's ongoing. Okay, I'm now coming back. So there is I'm going to talk about the deep circulation here. This is meridional overturning circulation, global, not Atlantic. And on the right is CESM2, on the left is CESM3. We had a very weak, deep cell here in CESM2, which was pretty detrimental to the ocean biogeochemistry. We're doing better in CESM3 right now, still pretty far from OBS, still pretty weak. So that's related to Antarctic bottom water formation. Happens down here, comes down and drives an overturning cell here. We also think that the strength of this is related to the ACC oscillations that we're dealing with. So we're hopeful that some of our tuning here with the ACC oscillations will also help improve this deep overturning cell. And then I alluded earlier with the Leith backscatter, Leith E backscatter, I alluded to some detrimental effects. And you can see on this slide, one of those detrimental effects, really the main detrimental effect, which is that there's a very large and spurious upwelling at the equator. There's a very strong overturning cell right here, which we don't see in observations or high-res models. So that is where we are. Summary. Mixed layer eddies. We used to use FFH in CESM2. We're switching to Bodner, but we've got it turned off in the Lab C. Okay. Lots of changes to the vertical mixing scheme, KPP, a lot of connections to waves, which is great. Also, Bodner is connected to waves. We have this stochastic backscatter for the mesoscale parameterization. We have another backscatter, which is not stochastic, which is improving BGC. And then in progress, we're tuning to try and improve ACC and also improve the bottom cell. And that's it. We'll move to discussion next. So I'm going to invite my fellow co-chairs to come up for the discussion. And for the discussion, I believe we're going to use the room mics. So I'm going to stop using this one.
This like feeder topics, but anything else means if you have something else you want to talk about. So I guess I'd say start if there are questions about CSM3 release or the components or CMIP 7 or whatever. Anyone else who wants to start the conversation? Don't be shy. I'm sure people are.
Yeah. Question just to start us off. I don't know much about the Labrador Sea issue, but have other modeling groups had that before, and how common has that been, and what approaches have they used to try and get rid of it?
I think it's been an issue for CESM since before I came here. I don't know if someone else can. Peter, how long has it been an issue for you?
Since we started.
Okay. And I know other groups have had issues with it too. I think a lot of it has to do with like it's this kind of funny basin, and when you're using low resolution models, you can't control the lateral gradients you need. I think E3SM
also had issues with Lab C.
Yeah, E3SM had issues. I think they solved it with resolution.
It is looking a lot better in our recent version 3 release. I'm not sure if I know the answer of what exactly solved it, but yeah, we've had a lot of updates. And so yes, it's been a pretty persistent issue across a lot of models, I think.
More regions, more models. I was just going to, it existed in CSM2 as well. There is no silver bullet. I mean, in this case, it's being addressed through the submesoscale mixing scheme. In CSM2, what we ended up doing is essentially we ran 3 ensemble members of the same configuration. 2 of them froze, 1 didn't, and we continued with that one that didn't. So, and one difference is that in CSM2, whatever we did, if a case did not freeze until year 106, everything was okay. In this case, it's not the case.
I was going to say too, can we get anyone online, if they raise their hands or chat, we'll get the configuration difference so we can see it.
I just want to add on the Lab C, that we never had any issue with higher resolution. So if there is one silver bullet, is that if you run higher resolution, you don't have that issue.
And ESM as well.
Can ESM also?
I think the atmosphere changed resolution too, though. So.
I mean, it's sort of implied like Gustavo's talk, but do we expect the precipitation to change dramatically in the upcoming development runs?
Against CSM2?
No, in CSM3, right? If I understood right, you were showing that there's too much precip happening.
Yeah.
Is that something that might change?
Unexpected. Yeah, this line, I don't think we solve the problem.
You could pipe it to the Amazon.
Yeah, the short answer is no, the precipitation, no, but Bill Lipscomb's here and they're doing these, fully interactive Greenland ice sheet runs. So at least we won't be getting the frozen runoff from Greenland as much in the fully interactive Greenland runs. And I looked at one of those that Gunter had done, and it does look pretty promising in terms of the fresh water getting into the labs. So.
Have you guys run no waves plus waves to look at what the impact of the wave ocean coupling is in CES?
Not recently.
It's pretty deeply embedded, so it's kind of hard to just flip a switch and turn it off at this point. You have to reconfigure the whole vertical mixing scheme to take account of the fact that it's not using waves anymore.
Yeah.
So we haven't done that.
I think on this coordinated experiments, it would be nice, once we kind of have a final version, to have at least some PI control for some period where we do try to turn it off just to see like what are the ocean impacts, what are the ice impacts. Maybe we freeze the lab sea immediately and that's the impact. I don't know.
Well, because when I did that experiment, I did see a big increase in ice in the lab sea where the wave ice impacts kind of negated it. I was wondering if you guys got sort of similar impacts with the wave coupling in the ocean versus not.
So the FSG came in very recently.
Yeah.
Right. Like a month and a half or so ago. Before we had Bodner off, and most of the runs, I would say 90% of them would not freeze. And there were, and I think it's related to the initial condition. We always start from initial conditions from a G case, and then I think I used a initial condition early in the GRA cycle. That was the case that Dave then ran for longer with FSG, which freeze and then unfroze.
Yeah.
But I would say that 90% of the runs that we did once we turned off Bodler in the Labrador Sea did not freeze.
Right. We did have this sort of interim thing we tried where we had only the one-way coupling, so we had wave attenuation under the ice. And in those runs, remember, it was freezing the lab sea quite a lot too. And so we were toying with the idea of having wave attenuation only when latitude was negative. And fortunately, that was when I got the idea to turn on the full FSD. So now we have wave attenuation everywhere. So
No, I guess I was just interested in the impact of the wave mixing stuff on the whole system. But it's a hard one to isolate for you. Yeah.
We'll have to return it.
Yeah.
Yeah, so basically just a related thoughts, right? There seem to be, once you have the wave ice coupling, you have now linear impact under the ice. Then you just showed your ACC issue seems to be not enough convection, but this might impact that. So there's like several balances now that can compensate or create the issue. And I think that it might be a weird sticky point where there's also like all this other surface forcing, catabatic winds that can affect it and so on, right? So yeah, I think maybe you, as I said, have somehow figuring out a coordinate set around that probably. I don't really know how to sort it out.
Yeah, it's possible that by attenuating the waves under the southern hemisphere ice, we improve the physics, but now we have less mixing, and so we have less release of the heat anomalies, and now all of a sudden we have an ACC problem, which is a classic compensating errors thing. Yeah. So we want to leave the close ice distribution and wave attenuation on, and then try to tune other things to fix the ACC.
One thing that is up for grabs, if you ask me, is what should be the wind energy input into the surface waves in the presence of sea ice. Currently, it's proportional to the sea ice concentration. There's no basis for that scientifically. So that's something you could tune. You could make it nonlinear, like and increase the wave energy. And if you want more energy in the waves, increase the wave energy and put in the presence of sea ice.
How's that done? So like you that's the stress calculation where you split up between stress goes in the wind stress goes in the ocean and then the waves, but I actually don't know what CSM does. There's no flow. Right. So all the wind stress goes in the ocean and you also drive waves. I guess so.
Yes, is the first scheme that Aaron showed before they modified. So that was the original.
Oh yeah, because the use of implementation.
If I can jump in, I had a question for Gustavo on the Lab C stuff again. The iceberg input you showed was pretty striking in the coupled model, and it seemed way too high. I was curious, where is that bias originating from? Is that like, do you have a balance with land precip and iceberg input into the ocean, I assume? So is it too much snowfall over Greenland that's causing that? Or are the icebergs advecting erroneously into the Lab C preferentially? And then a follow-up, have you done any sensitivity tests where you either turn the icebergs off or force them to melt quickly or something just to reduce the freshwater input into the Lab C? And did that help this issue?
Image. We don't have an iceberg model. So what we do is the same way we do with rivers, we just spread the frozen runoff using a specified radius and a decay for that spreading. So in a way, like it's a crude way of simulating icebergs, but there's no icebergs models like in the GFGL model. And you're right, that is coming from a bias in the precipitation over Greenland, and then gets routed to the rivers and then sent to us. Yeah. Actually, the frozen runoff, it doesn't get routed to the rivers. It's just like this bucket. Once the ice reaches above 10 meters or so, I think it gets sent to the
Yeah, it's a snow capping.
Snow capping, yeah.
Okay, so do you suspect if you rerouted the rivers, to run into the Greenland Sea, for example, then this issue would go away?
Yeah, well, we try, like we didn't reroute the rivers, but we changed the way we do that spreading, and that helped. So that was more than a year ago when we first saw that the Lab C was freezing rapidly. We started playing with these radius of spreading, and that was it helped initially. So by not spreading all the way in the middle of the Lab C, but keeping the liquid runoff and frozen runoff confined to the coast, which that's what nature shows, it helps avoiding the freeze, but it didn't solve the problem completely. We had to do these additional things in order to avoid the freeze.
And I will say, Mitch, in CESM2, we tried lots of stuff like all of the runoff from Greenland, we put it up into the central Arctic and stuff, and that was not successful then. So we didn't necessarily try all of those again this time, but we have tried things like that in the past.
I think Ed had his hand up. So we'll do Ed first and then in the room.
Ed
Blanchard.
Hi, can you hear me?
Yes.
Perfect. So I wanted to ask about Dave's point that the Antarctic sea ice in the summer is bias low, and that was in a pre-industrial run, right? And so I guess two questions. One is, how concerned or how much of a kind of showstopper is it if by the end, when you run it with like a deck, like 20th century historical forcing, what happens if like there's no summer sea ice left by the year 2000? And you could think how that could have some downstream impacts on like the Antarctic continent, right? Like making that too warm. So I'm wondering if you've thought about ways that maybe we could target that. And I was thinking about how Jen Kay, her paper a couple of years ago, when she targeted in CSM2 that the Arctic sea ice was too thin, right? And she changed a couple of parameters. Yeah. We're kind of pretty much fixed Arctic sea ice without really affecting or degrading climate elsewhere. So that might be one way to go about it. And I guess the other thing is that I don't know if you had a chance to see whether that bias in Antarctic summer sea ice, if it's at all related or influenced by this really kind of large variability in the ACC.
That's a lot to unpack.
Yeah.
So I thought about it.
I think a couple points, and I'm sure I'll miss things, but the seasonality though, like it still gets really thick in winter and pretty extensive in winter. And then even in the 20th century runs, we see that the ice doesn't completely go away in summer around Antarctica. So I guess I'm not that concerned about it. I mean, it would be nice to try to bring it back. And then on your point about, the less melt runs that we did in Jen's paper, that works really well for the Arctic. It does not do anything in the Southern Hemisphere. So we can't just tune that to bring up the volume in the Antarctic. So, but then your final point is maybe it's not really related, it seems, to the.
I looked at the time series.
Yeah.
The 2 seasons.
Yeah, it doesn't seem to be related to the ACC variability.
So, and bottom line is, I think it's probably a bias we have to live with because we haven't been able to do anything that includes it. One thing that the oceanographers were planning to test for the ACC, I don't know if you've started this, is this spreading radius. And so they were going to bring it back closer to the coast so it's less like out over the Weddell Sea or the Ross Sea. So like maybe we'll get thicker coastal ice and it'll stay around longer, but we're not sure. But for right now, like last year this time, one of the, the showstoppers was that our Antarctic sea ice in the winter was like way too extensive, and we were able to address that as Ian talked about, but we haven't. It's been like this for a long time and we haven't been able to do anything. So just like the Amazon's dead, we may have no sea ice this summer.
Well, it didn't stop some CIMIP 6 models from going ahead. So I remember the Miroc model, like some models in CIMIP 6 are very, like almost no Antarctic sea ice, right? Or very little. So
Right. Follow up on this.
Yeah, I was wondering if you did any runs where you varied the blowing snow parameterization.
That I haven't done.
Look at that.
Maybe increase the snow cover on the Antarctic ice. Yeah, maybe.
And see if that's causing.
Yep.
Although if the blowing snow is compensating for far too much snowfall in the Arctic.
Yeah, I agree. But I'm also worried about, overdoing it in the winter. So
we can do some tests with that.
Yeah, but we can test it.
Regarding the lab C, I'm wondering what are the trade-offs you have of like turning on and off Bodner? And the second is, what are your thoughts? I know it's like a resolution thing that sometimes like the continental shelf can like constrain fluxes from the continent into the ocean. And I'm just wondering, what are your thoughts about these two topics?
I think that having a parameterization where you put a mask and turn it off in a particular location, it's really ugly. We're not happy with that. But on the other hand, that particular parameterization was not developed for a place like the Labrador Sea. It was developed using LES for the Southern Ocean, open ocean conditions. And the Labrador Sea is a completely different environment. So we can argue that it is not doing the right thing in the Labrador Sea. And that was the second question.
Regarding resolution, because I know you cannot run at a high resolution, but I was just wondering, what are the effects of not having like a proper continental shelf description in terms of fluxes exchanges between like a shelf and slope?
Yeah, I think, and I tried to mention earlier, in the high res, this is not a problem. In the low res, like the representation of the coastal current being confined, and then also having warm water from the North Atlantic getting into the Labrador Sea. We always have that so-called cold wall bias. You see in a couple models that you don't have enough warm water going northward, making into the Labrador Sea, for example. That is a problem with low resolution models. Yeah.
Follow-up is we're thinking about having different configurations for the coupled and uncoupled cases. Mm-hmm. So in the case that's ocean ice, we're just going to have Bodner on everywhere. I think one of the things that we lose when we turn Bodner off is the location where deep convection happens in the lab C. It tends to be kind of in the wrong place when Bodner is off. When it's on, it shifts it more towards Greenland, which is more accurate.
It's the other way around.
The other way around?
or the other.
Yeah.
So there are some drawbacks to doing that, but of course, in the coupled case, it's more than offset by not having the lab C foods.
Right. I will just highlight, we've toyed with the idea of variable resolution in the atmosphere model, because it's pretty easy to do that. And so we have like this Arctic high resolution domain we've played with in CAM. The problem is MOM and SICE are not really configured to do variable resolution at this point, but that would be another nice way to deal with this.
Dan?
Understandably, it seems like a lot of the tuning targets are based on the model mean state. I was wondering, I mean, with the notable exception of the ACC ringing, and so I was wondering if, like for instance, the stochastic backscatter could have any implications for ocean variability, given that CESM is used so much for ensembles and marine heat waves and extremes.
Yeah. So our standard diagnostic suite doesn't have SST variability in it. I do look at that from time to time on my own. The CBDP package does look at that. And so we do get, it does affect the variability. The stochastic backscatter, the other backscatter, the deterministic one, also affects the variability. There's pluses and minuses. I'm not sure if I want to say definitively if it's a benefit from the CBDP diagnostics. I will say that Kate Bowden, who's a student working with me, is investigating the impacts of this on data assimilation, ensemble data assimilation, and her talk is tomorrow. So come to that if you're interested in that.
I guess along those lines, at least in the project meetings, Adam Phillips, who frequently presents on CBDP, we haven't had too many really long runs, but there hasn't been anything that's like, this one is nuts. So, I mean, trying.
Yeah, the leaf backscatter scheme tends to reduce SST variability that you compute using monthly means, so not fast time scale, right in the tropical equatorial cold time in the Pacific, which for our other development simulations is indeed improving a bias. I mentioned this at the OMWG meeting, and somebody said, oh, it's worse, it's lower. And I went back and verified, indeed, it is lower, but it's also better.
Like I saw a hand earlier.
I was going to comment on this reduced precipitation over the Arctic, and just to let people know, we have tried, or the atmosphere model working group tried, and they tried. I think the source problem is too much evaporation from the oceans, kind of just generally, and then that's the way you have to try to approach it.
Now they're blaming us.
No, I don't think it's a blame with the ocean.
It's the landmark. It's landmark.
But when they did make some changes that reduced evaporation over the oceans to something that seemed more realistic, and then other things just went so crazy, it was like not really viable. So it's something I think we want to pursue for the next generation model to really try to get at this problem, but it just was way too far. And so went Blackie and MJO and everything was like, precipitation was really weird. So, yep.
Just add shortly on that point. I mean, we've been working with the folks down the hill at NOAA looking at in situ morning-based flux observations, comparing those with the models. And even the reanalysis systems show excessive evaporation over the ocean. So there's seems to be some sort of systematic problem in the representation of atmospheric boundary layers. Think of us, we're pumping too much water vapor out of the boundary layer into the pre-troposphere. So the integrated water vapor is too high, but the boundary layer is too dry. And this seems to be a pervasive problem across models.
Right. Since we were talking about this transport of fresh water from the continental shelf into the ocean, I just thought, since we're in a coupled model, how much does this feedback of not having a continental shelf would influence the open ocean? Because you have basically water coming from continental shelf and going in some cases straight into the open ocean, and then it starts mixing. And then it would create like an evaporation bias because you have more water in there, and then it will precipitate more, and then the cycle will start to roll, you know.
Yeah, but I think the issue is that the excess precipitation comes from south, the way south, and gets transported northward. So it's not that localized, that there's a local feedback going on. Okay. If I understood correctly. Yeah, that's it here.
Nobody's brought this up yet, but I want to make sure that we talk about it. So the coordinated experiments analysis comment, we had some discussion this morning about wave experiments, and Aaron mentioned one about turning off waves. This spring, we have the CSL proposals again, and the procedure is going to be a little bit different this year in that, like, we still welcome proposals for experiments from anyone here, but we don't have to provide quite the level of detail to sizzle. So, Polar Climate Working Group will get some resources, but we do need to plan and figure out what we support in terms of like big experiments. So one question is, it's unclear if there's going to be a CSM3 large ensemble or something like that. And would people want something like that? Or, so there should be still, the ability for individual researchers, postdocs, research groups to do experiments, but CSM3 is more expensive and we have limited resources in that way. And so being able to plan what we might want to put some of our resources towards, like a larger ensemble or whatever, would be helpful. So if people have comments about that, I think that would be helpful for us in terms of planning. And then same with if you have a strong opinion about anything other than the deck, we must do scenario ML, whatever it was. I think knowing that, or if you have thoughts about that, that would be helpful. Because I don't think CNET has actually released all of the forcings yet for like scenario net and stuff like that. We're not behind anyone. We're just going at the pace we can.
And also on the OMWG, there was supposed to be a meeting 2 weeks ago that got canceled. So I don't know if they have any broken.
Rita is going to talk about it tomorrow, so we can discuss that thing tomorrow.
Like, how many people would like there to be a CSM3 large ensemble-ish, if possible?
Education.
Oh, wow, you've got a spare billion computer hours.
Doesn't happen on the same time scale.
I think so.
You guys didn't mention the cost of CSM3 though, right?
Yeah, that's because I don't know what it is with the new level.
It's higher than CSM2, I guess.
I said it's expensive. You have to ask, it means it's too much for you. All right, so there's support for some sort of ensemble, maybe not 100 members, somewhere, there's questions about what's the right amount, but some number of like, I don't know, 30 to 50 or something like that. And for people to be able to use as almost a baseline for community experiments or something else. There is support for that.
I think we talked about this last time. There was some discussion about like time period. Maybe I asked this, like, can you do a large ensemble for a smaller time period?
Yeah, I mean, I think there'd be questions about how it's done. Like for the CSM1 large ensemble, it was 1920 to 2100 to help with the cost. And for CSM2, it was 1850 to 2100. Maybe we run, this is just an example, like 10 experiments all the way from 1850 to 2100. And then we have smaller bursts at whatever, where you have a lot more. I think all of those are possibilities, but it sounds like people would be interested in some sort of group of ensembles to be able to compare against details pending.
Yeah, I mean, I don't know if this is quite the right forum, but I do think it'd be very interesting to do some sort of perturb parameter ensemble with, there's a lot of knowledge about which tuning knobs are helpful and not helpful, but actually putting that into a set of simulations would help people figure out, where we need to focus.
Right. Yeah, and it's recorded. So.
Are there plans for the CNET 6 force runs?
I don't think that there are specific plans for that yet, but if there's support in the community, just like Marika led a CSM2, CNET 5 ensemble, would people like a CSM3 CMIP 6. Try to get my numbers right here. Is that some, if you had to choose ensemble versus that, what would you choose? And then there is a lot of logistics that goes into like, we want to run CESM3 with CMIP 2. There might be some challenges with how to make the forcing happy.
So far, don't seem to be as different this time as far as I can see so far. Compared to, there was a really big difference between CMIP 4 and CMIP 5 or CMIP 5 and CMIP 6. I'd like someone else to confirm that, but that's my sense. When we switched, we didn't see like a big difference in the simulations.
Ed?
On a similar note, I'm wondering what the thoughts are or what to do with the biomass burning. Because I know Patricia and John Fasulo showed with CSM2 how what a big impact that could have, especially in high latitudes, in the Arctic. And I don't know yet what the CMIP 7 future or like 21st century biomass burning scenario is going to look like. As far as I understand, the historical posting files are going to end in 2021, which is kind of one of the peaks or, biomass burning in boreal regions peaks. And so I don't know how that transition is going to look like in the posting files, but, I'm remembering that kind of funny feature that CSM2 had, right, as it transitioned. I think we should be aware, or at least attentive to that.
I will say, I think that there's been, like, Isla has done a lot more with getting forcings and basically like making sure everything looks reasonable so that we don't have weird transitions. I don't know that we have an answer yet, partly because we haven't decided on a scenario. I'm not even sure I haven't been deeply involved in the scenarios, but they're not even released yet, are they? Like, is the forcing released for the scenarios? No. So, but I think it's a good point. We can keep it in mind when we choose whatever scenario we might do to make sure that this transition is not super abrupt and looks like do some testing on that maybe first before we figure out how we want to transition.
We will be smoothing the biomass burning for sure.
Okay.
Either they're going to provide the data set. It's unclear what.
Well, I mean, they're aware of the situation, so I suspect that they'll take care of it.
Yeah, they're being a little waffly as far as I can tell, but also we're also, I think, smoothing a few more of the emissions files that they had in training. I went from smooth to high infrared variability. It might have less of an impact, but probably still aliasing onto things. So at least I've asked the team to just say, let's just make the decision to we're going to smooth everything because it's not really a realistic thing to do. So anyone really doesn't like that idea, that to hear from it, but probably it's more going to the chemists who would care about that. We also have the capability to run with interactive biomass burning emissions, and probably not going to do that for the default, but we probably will have a configuration.
And again, I think if we have some kind of baseline set of simulations, medium ensemble, whatever we want to call it, and then you want to run a non-smooth version, you can compare. Like if that's something you're interested in, Ed, we could compare how big a difference it makes, but that might not be the default. All right. A few more minutes. Any other burning things people want to talk about? Everything the mid-afternoon.
Unintended.
Sure. Any freezing things you want to talk about?
Alice, I don't know if this is the right moment, but I know you mentioned Cupid, right? Is still under development. And I ran it myself a month or two ago, and there were definitely still a few kind of issues with it, especially for like single run, like the way it's set up by default, or at least 2 months ago, was to compare with a base case, right? So you had to kind of edit it if you just had your own run that you wanted to post-process. And then I think the ability to do like monthly and daily maybe wasn't quite there yet. It might be now, but I'm just pointing that out because there might be other users that kind of run into those issues. But I'm sure the Cupid team's kind of aware of that.
Thank you. Just thanks for letting us know and letting us know that you ran it. I think it's hard to maintain a diagnostics package that works for everyone. And like Dave and I have done a lot with what we have, but if we don't get feedback like this, then we don't know what doesn't work. And Yeah, go ahead. Mike is leading Cupid stuff, so.
Yeah, so I will say that we know that the time series generation, I think that's what we're talking about the different streams. Like that's an issue that we're working on. We're going to replace the tool that generates the time series and put in something more robust and fix the API so you can't generate time series.
Exactly. Yeah. So I wasn't more clear about the time series generator. Yeah.
Yeah. So that'll hopefully be changing like in the next week or so. And I guess I'm a little surprised that you can't just set the base case to none and turn off all of the baseline comparisons. That might be something that I thought we did that we never actually did. So I'll look into that.
Mitch?
Yeah, I was curious to hear a bit more from Ian, maybe, and Gustavo about this ACC issue. So you mentioned you had a couple of ideas for improving this, like these big swings in the ACC. What exactly are you playing with? And I think you both know that we've had a lot of these issues at GFDL as well. Very similar sort of linear ACC, sea ice, sort of centennial scale variability. This looks a bit bigger than what we typically get, I would say. But our fix has been increasing the land ice albedo over Antarctica, which increases intermittent convection in the ocean, which chews up the subsurface heat reservoir. So yeah, just curious what you have in mind and if anything's worked so far for you.
So one thing we found a bug a few days ago. We intended to set a minimum for the Rayleigh coefficient throughout the whole water column. And there is a flag that says ensure minimum is applied in whole water column, but it only assures that it is applied within the boundary layer. So the neutral diffusion part does not have a limiter in the minimum Rayleigh. So with the vertical structure, it actually can go to 0. So we're not doing enough mixing below the boundary layer, horizontal mixing, mesoscale mixing. That is our kind of, we had a few runs going, like 2 of the runs are trying to target that. So we fixed the bug and now we're playing with 2 different minimums. One is 50 meters per second, and one is 200, with the hope that we'll be mixing more and then avoid the buildup of heat and depth. And then the second one, we briefly mentioned that we're spreading the runoff differently now. So the default is, I think, is like 250 kilometers, which a lot of freshwater and frozen runoff goes into the middle of the Weddell and Ross gyre. So similar to the lab C problem, it is shutting off or helping shut off convection. So we are now using a smaller radius, 100 kilometers, with the hope that fresh water will be confined, again, along the circumpolar current or the Antarctic circumpolar current, Antarctic shelf current, thank you. One of these coastal currents, and now go into the middle of the gyre and shut off convection. So those are the 3 runs that we have going.
Also vertical mixing, right?
Oh yeah.
Also, yeah, we also tried a bunch of things that didn't work that might be useful for you to hear. So we tried reducing the bottom drag coefficient to speed up the ACC. That had minimal effect. We tried reducing the GM coefficient, and that actually does have an effect. That actually takes you from blue to orange to gray here. So reducing the GM ready coefficient improves things, but it also has other detrimental effects. Classic one is that the SSTs get colder when you reduce the GM coefficient, and it has effects on restom. And so that's about as, we do think that if we reduce GM further, it would help that, but the knock-on effects on other things are more than we can stomach. So that's as far as we can go with reducing GM. We also tried the bottom boundary layer efficiency thing that you guys changed in CM4X, and that didn't do anything. What else did we try?
The vertical mixing.
Yeah, we increased the background vertical mixing, and that had that's great. That's this one. So it has big positive impact on keeping the ACC in range, but it screws up so many other things. So we can't do that. So we're now thinking about selectively increasing the vertical mixing just around Antarctica. I'm curious, what's the mechanism? Because all we've tried is ocean tuning knobs. And you talked about the land ice albedo. What's the mechanism for that?
So, I mean, the blend, it's a bit of a red herring, I think. It's basically just anything that changes the surface energy balance over the Southern Ocean. And so the effect of the land ice albedo was to cause Southern Ocean cooling, which generally destabilized the water column and just prevented those big subsurface heat buildups. We still get them, but it at least mutes them quite a bit. So I think anything that would cool off the Southern Ocean a bit, but then you tend to have positive sea ice biases. So there's a lot of a lot of negative effects that you have to kind of stomach as well. So we're constantly fighting this balance between getting enough convection and not being too cold in the Southern Ocean. So we really struggled with this problem as well.
Well, thanks for telling us about it.
Maybe it would help with our summer sea ice bias, though.
There you go.
I think in a lot of I'm kind of joking, but I'm kind of not too.
Yeah, maybe we can go back and see if the summer sea ice ever looked very good, but it's been.
Well, just if we have a higher land ice albedo.
Oh, the albedo
will cool, especially in the summer, how do you feel about that, Bill?
Is it,
There might be
is
an
it
impact.
actually land ice albedo or is it snow?
Well, I think in Mitch's case, it was the albedo over Antarctica. So it might have been the snow albedo. I don't know, Mitch, can you?
Yeah, it was the near infrared snow on glacier albedo in our model, and we made it brighter, and then that seemed to do it.
We don't have a snow on glacier type. We just have snow.
Right, you have a bead.
So we would have to change all snow.
There might be. I mean, there's bare ice, right? I don't know what the fraction of bare ice. There's no bare ice.
We can just change the snow over Antarctica. Latitude is less than.
Just so we can take the ocean strategy of making boxes.
Latitude negative.
Another wave possibility is there is a nonlinear source term in the wave model that's multiplied by sea ice concentration, which doesn't make any sense at all. So there's stupid things in the wave model throughout all the sea ice, but I don't know whether that would, it's a matter of moving energy across the spectrum. If it would help mind.
Yeah, maybe we should talk.
Yeah, we just didn't want to bug Wave Watch 3 developers with too many things at once, and so we never mentioned it, but it is wrong. Badly wrong.
I also want to point out it's 3, so we probably should stop and take a break because there's only a 15-minute break. So I guess if you have other comments, come find one of us, or we'll have discussion tomorrow as well.
Ocean is back here at 3:30. Ice is in the air.
Yeah.